Oh, da. That's very little Welsh that I've been able to pick up so far in my few hours here since arriving yesterday afternoon. Good afternoon, ladies and gentlemen. Good morning. Yeah, I ought to learn to speak English properly before Welsh. Yes, it is morning. I'm the president of the BAA, David Arditti. Thank you all very much for coming. We've had a few problems with this meeting. There's been train strikes and there's also been a flood here at the museum, which resulted in the bigger lecture theatre, which we were booked to use, has actually got flooded. So we are in this room today, although this room might be indeed more suitable for our purposes because it's a bit more intimate. This meeting has been organised by Hazel Collett, BAA's meeting secretary, very much in collaboration with the Cardiff Astronomical Society, and we have the chair of Cardiff Astronomical Society, Philip Wallace, here today. I managed to get here by train, surprisingly enough, yesterday, despite the strike. I don't know Cardiff very well. I have visited Cardiff Astronomical Society once before, a few years back, when I gave a talk about what astronomy can be done from the city. And I was treated very well by the society. I remember being shown through, the best way to walk through Cardiff was through all the shopping centres. So I had the first thing I had was a tour of the shopping centres of Cardiff, and we were taken to a fish and chip restaurant, which is recommended by Professor Alan Chapman, and that's apparently the best place to get fish and chips in Cardiff, and it comes with his imprimatur, which is saying something, and what he doesn't know about fish and chips and cups of tea isn't worth knowing. So, more to the point, Hazel has assembled a galaxy of experts on astrophysics, cosmology, the origins of stars and things in the universe today. So we're very lucky for that. And we will also be told a little bit about the Cardiff Astronomical Society, which seems to be a very active society, one of the biggest in the country. We'll hear a bit about that. So would you like to say anything, Philip?
Yes, just say good morning everyone, welcome to Cardiff. As you can probably tell, this is not where I'm from originally, but I have been down here for 13 years now. Like so many people, I came to Cardiff to South Wales University, and then for reasons that made sense at the time, I stayed. There have been days when I questioned my sanity, but that's actually fairly normal for me, as some of my colleagues from Cardiff can attest. Yes, I'm glad so many of you are able to make it here, despite the tribulations that we seem to be experiencing. As David said, Cardiff can be a bit of a maze. We usually reckon it takes you about 4 or 5 months to learn your way around, and by the time you've learnt where it is, they've built something new, so you have to learn it over again. So never ask a Cardiff person for directions, useful tip that, because they will refer you to a building that no longer exists or has not yet been finished. I must say, we have, Hazel has put together a truly excellent programme for this. We've been involved planning this for some time. So I say we've been involved in planning this. Hazel's done most of the organising for the speakers. We've just been providing local knowledge and organisation on that front. So I'm very much looking forward to these talks, which seem very interesting, and I hope to poach 1 or 2 of them to speak to Cardiff at some point in the future. We can never quite turn off this whole networking thing. We're always looking for speakers. So if anyone's interested, please see us afterwards. I'd like to say thank you to my volunteers who are here today to help as well. Teresa, Greg, Joan, Siobhan, Jane and Kath. They're all much appreciated for their assistance in setting things up. And as David said, we'll have to hear a bit more about the society later on, once we've had lunch. So if the lunch doesn't put you to sleep, Greg and myself talking about the society probably will. But we will wake you up in time for the afternoon talks, so no worries on that front. I think that's it. So thank you very much. Enjoy your day, everyone, and good to see you all.
Thank you very much. do we have Dr. Nicolas Peretto here?
Yes, I'm here.
You are here.
Excellent.
Right. Dr. Nicolas Peretto is, where are you from? Are you French?
Yes, I am.
Yes, he is from, he did his PhD at Pierre and Marie Curie University in Paris, and he studied during that period the collapse of NGC 2264, star-forming cloud. He then went to the University of Manchester to do his postdoctoral studies, and then he went back to France to their Alternative Energies and Atomic Energy Commission on a Marie Curie fellowship. For the past 10 years, he's worked here in Cardiff. They've got an astrophysics research and technology centre or hub at Cardiff University, and that's where he's been. And he's an expert on star formation within the Milky Way, specialising in the kinematics of infrared dust clouds. We're very pleased to have you here today, Nicolas, and he is going to talk about the formation of stars from sunlight to the most massive ones. So, go ahead.
And to swap, I just press on my computer, or do you have something? Okay. Thank you very much for being here, having me here. Last time I gave a talk at the BAA was in front of my computer during the pandemic. I much prefer seeing all these young faces in front of me. That's much more pleasing. So as that has already been said, I'm going to talk about the formation of stars, from stars that look like the sun and those that are a lot more massive, from 10 to 100 times more massive than ours. Obviously, in 40 minutes, you cannot address the topic of star formation in its entirety. And therefore, I had to make choices, and when you make choices, you have to, your biases basically come into play, right? So this is going to be a biased view of star formation, which is with my own biases, but I think my biases are probably the good ones. Anyway, let's move on. So let's start from home, right? The sun. So the sun, as I'm sure all of you know in this room, it's about 4.6 billion years old. It's at a distance of 150 million kilometers from us, which is also one astronomical unit by definition, and it's 1.4 million kilometers wide. So just to put things into perspective in terms of sizes, here at the bottom corner is the Earth. Everything we know of that we can deal with is on here. Now this is not to scale. If you want to make it to scale, it's something like that, right? So just to give you a perspective. So we are dealing with this type of object, stars that are really, really massive, and the sun, as we're going to see, is not the most massive one. So when we look at this movie here, so this is a SDO mission movie that has been obtained, in fact, from the 9th of May to the 11th of May of this year, so it's only just a couple of days old. What you can see is an amazing complexity at the surface of the sun, where you have filaments that keep moving, changing in shape, you have eruption, you have a lot of things going on the surface of the sun and also inside the sun. However, despite that complexity, we know and we understand pretty much the physics of stellar evolution. We understand, for instance, that the reason why they are not collapsing to a point is because they are in something that we call hydrostatic equilibrium. Right? That means that self-gravity of the star, which try to put everything, to collapse everything to a point, is prevented to do so by the pressure gradients inside the sun. Right? So at the center of the sun, you have nuclear fission. Hydrogen is being burned into helium that releases a huge amount of energy, and that energy helps to maintain the star as it is. So that's great, we understand that. And the thing to realize is that the only parameter that will predict what's going to be the end life of the sun is its mass. And this is true for all the stars. What I mean by that is, if we know the mass of a star, we can tell it's going to end up as a white dwarf, as a neutron star, as a black hole. Right? And that's the only parameter that we need to know. The mass for the sun is 2 × 10⁻30 kilograms, which is what? Which is 2 billions of billions of billions of tons, something like that. So it's a huge amount of mass. And knowing that it has that mass, we can tell already that in 5 billion years or so, the sun will turn into a white dwarf. Okay, so if the mass of stars is so important, how does the sun compare to the global population of stars? Is it a relatively low mass, high mass? How does it compare to the full population? What you have here on this slide, on the left, that's the left for you. That's the Pleiades cluster. Everyone knows that cluster. You can see it by the naked eye. Actually, there's a very similar pictures at the very end of this room. Yeah. This is a young cluster. It's a few 100 million years old, which is young in the context of stellar evolution. And now if you play the game of identifying each star in that cluster and measuring its mass, then you can plot the mass distribution of these stars, which is what you have here on the right. So here is nothing else than the mass of the stars versus their numbers in each mass bin. Right. So this is a log scale, so the sun is here, that's the red line, that's the mass of the sun there. And you can already see straight away that, well, there are stars that are less massive than the sun, and in fact the most common star that we have in that cluster is about 0.1, 0.2 solar masses. But you also have more massive stars than the sun. In fact, the blue stars that we see there are all more massive than the sun. So overall, when you see this, you can say, well, the sun is not a very massive star. We can categorize it as a low mass star, but it is not the most common type of star that you see either. So the thing to realize as well is that if you were to do the same job, plotting the mass distribution of stars in any cluster in our own galaxy, we will obtain exactly the same shape of the mass distribution. And this is quite unexpected, in fact. So wherever you look in the galaxy, whether it's in a cluster or even field stars, so stars that are not in a cluster, and you find a way to measure the masses and plot their mass distribution, you will have the same shape. And this is the topic of a huge amount of research in star formation. Why every time we measure the mass distribution of stars, we get the same thing. So that's why we said the stellar mass distribution is universal. And even as of today, we see there are many theories that try to explain why we get that shape, but there's not yet a consensus about it. So now understanding the fraction of, for instance, low mass stars versus high mass stars is massively important, not just to understand what's going on in our neighborhood or even in our own galaxy, but also in other galaxies. The reason is the following. So given the shape of the mass distribution of stars that I just showed you, the mass of stars is in a galaxy, and any galaxy is dominated by low mass stars. Right? The reason is because there are a lot more of them. But the luminosities of galaxies is completely dominated by the massive stars. And the reason is that if you have a 10 solar mass star, that star is more than 1,000 times more luminous than a 1 solar mass star like the sun. So even though there are not as many, they completely dominate the luminosity, the light that you see in any galaxy. And when you have so when you have the combination of these two, you can tell that the exact shape of that mass distribution will definitely regulate how a galaxy evolved across cosmic times. So understanding how and where this mass distribution of stars comes from is fundamentally important in astrophysics. Now, the one process that determines this mass distribution of stars is star formation. Right? It's the process that forms them that determines what the mass of the star will be. And so that's why star formation is so important. Okay, so now that we understand that star formation is important, the first question that we might ask is, where do they form? What you have on the right here is a visible image of the sky. Each white spot that you see here is an individual star. And what you can also see in the image are these dark shapes that you see there. So those initially were believed to be holes in the sky. Right? That was already observed even before 1919. It was observed already in the middle of the 19th century. They were not catalogued until Barnard did in the early 20th century. But it's only a few years later that, in fact, instead of being holes, we understood that it's not that there were stars missing, it's that there was something in front of the stars that was absorbing the light of the stars that are behind, right? And that thing is what we call interstellar dust. It turned out that there are a lot of interstellar dust in the galaxy, in all galaxies throughout the universe. I'm not going to go into details of what that dust is. If you have questions, by the way, if you have questions at any point, I like to be interested, so don't hesitate to ask. So the reason why we have these dark shapes is because there's dust absorbing the background light, right? And the thing is, just this image already tells us two things, right? It tells us that that dust has to be cold. The ability of any object, whether it's a tiny dust grain or whether it's a star, what determines the ability to emit light at any given wavelength is their temperature. So for a star like the Sun, about 6,000 Kelvin, it emits mostly in the visible. A dust grain, turns out that their temperature is about 10 to 20 Kelvin, and they mostly emit in the far infrared. Right? In the visible, they don't emit anything. The only thing that they do is that they absorb light or scatter light that comes behind them. The other thing is, if you look at B68, for instance, which is that tiny object there, it's completely dark in the visible. You cannot see a thing through it, right? You can spend hours and hours and hours of the best visible telescope, you will not see anything behind that thing. You will not see a single star. And so, in order to achieve that, you need a lot of dust, right? So you need a lot of cold dust. So we know that these dark things here are dense, cold pieces of interstellar clouds. So now if I move forward a few years, maybe a few decades compared to 1930, the difference between 1930 and today is that technology has allowed us to look into these things. There's so much you can do in the visible. When you look at an image like that, you can tell, for instance, that some of these clouds have certain shapes. You have areas that are denser than others, but you cannot do much more than that. Right? What we want to be able to understand what's going on in these clouds is actually to see their emission. And as I said before, dust is something like 20 Kelvin, which means that they mostly emit in the far infrared, and which means that we need technology which is able to detect that light. And that technology only really came along after the Second World War for radio astronomy, and for everything which is infrared, more like in the 80s, mid-80s, end of the 80s, and then forward. So star formation, observational star formation, is quite a recent topic, in fact, just because of technological development. So now, what can we see in this cloud? So on the left, what you have here is another dark cloud. This one is Taurus. It's part of the Taurus molecular cloud. You can see there's some dark shapes here. Again, it's the same thing. You have dust in front of the background stars, absorbing light, and therefore it appears as a dark structure. And now the same cloud, exactly the same area, but seen at 850 micron. Right? So now what we do see here is the emission from the dust grain. And you can see already that we can clearly and nicely see a lot of structure. We see a filamentary structure. There's a lot of substructures, some arcs, and some brighter spots as well. Now on the right-hand side, it's the same again cloud, Taurus, exactly the same area, but seen at 250 micron with Herschel. the Herschel, so Herschel, not Herschel the man, Herschel the satellite. Right? So Herschel was a observatory sent into space in 2009 that observed the sky in the far infrared, so perfect for star formation studies, and worked until 2013 and collected a huge amount of data regarding star forming clouds. Not only, but also. And you see that, I mean, even though this one is a really good image obtained from the ground, this one, you can see there's a lot more structure in the Herschel image, and the reason is because there is the atmosphere between us and this object. The atmosphere is quite bad for star formation study. It tends to absorb a lot of, not absorb, sorry. The sky itself tends to emit a lot of light, which is most of the time stronger than the light that's coming from the source that you are looking at. And therefore that creates issues. When you are in space, you don't have that issue, and that's why the Herschel image, there's a lot more structure in it. Anyhow, what we see here is that these dark clouds are basically very bright in the far infrared, because they are therefore emit in at these wavelengths. They are filamentary, at least that one, but most of them in fact are filamentary. And they're also fragmented. So what I mean by that is that you see you have these small spots here that you can also find in the Herschel image. And this type of fragmentation, you find them in any dark cloud that you are going to look at. So for instance, that's another example. This is in Serpens, a well-known star-forming region. And what you hear is again an image at 850 micron, so showing again the cold dust in that dark cloud. And here you can clearly see you have, so here you have isocontours that just show values of contours of constant values. What you see in this white bit is a peak of emission. Peak of emission means peak of density, of amount of dust that you have at that particular location. So there are basically more, there's a dust concentration here, and there, and same there, right? Now if you look at that same cloud, but at a slightly different wavelength, so now we are looking at the same region. This is a combined, it's several wavelengths in that image, but it's what we call mid-infrared from 4 to 24 micron. You can see that now you have this red kind of spot. These red spots are young stars that are currently forming, still accreting mass, still growing in mass, that are located exactly inside this cold, dense envelope of dust and turned out gas as well. Right? So if we overlay the small region that is in the top right corner, so this is the same thing as there. And now if you overlay, you will see that most of these young protostars in the mid-infrared are embedded within these envelopes that we call cores. Right. So we can say, we're quite certain that stars form in dense fragments that within dark clouds that we call cores for simplicity. Okay. So over the years, let's say in the past 30 years or so, people who studied star formation came up with some kind of empirical evolutionary sequence for how a star forms. So, and that's purely based on the type of images that I showed you before, and others obviously. Here I just showed you a tiny sample of them. So we start with what we call a pre-stellar core, which is something like that. So this is the same again as an image at 850 micron, the same wavelength that I showed you before. It shows you that you have a peak of emission here, which, as I said before, means that you have a peak of density. The matter is being concentrated there at that particular location. It's something like 20,000 AU, so the size of 20,000 times the distance from the Earth to the Sun. So it's quite large, right? And it's completely deprived of any stars yet. It's just a dense piece of cold gas within a dark cloud. Okay? Then at some point, that pre-stellar core, for some reason, and it's not, the reasons of that are not clear. There are, again, many ideas, but that piece of dense cloud will start to collapse on its own due to its self-gravity. Right? There's a mass now pressure are not able to stop it, it will start to collapse on itself. As it does so, at the very center, in the second stage, there's a small red dot there, you will start to form what we call a protostar. So that's the birth of a star when you have this thing. This thing here is actually a tiny piece of mass which is in hydrostatic equilibrium, which means that you have at the center of that core which is collapsing, you have something which has managed to stop the collapse. So it's not that red thing is not collapsing on its own, it's just stable because it managed to prevent the collapse of that tiny piece of mass at the center due to pressure gradients again. Its internal pressure is able to stop the collapse there. But the rest of the envelope is still collapsing onto it, and so it grows in mass. In many processes in astrophysics, when you have accretion onto something which is compact at the center, you also have ejection of matter. That's true for protostars, it's true for black holes, it's true for many types of objects. And so often, when your core is collapsing, you have a protostar, then you have a jet. So here, for example, is an example of a protostar, a young protostar, where your protostar is right at the center here, and you have this blue and this red thing here. Blue means blue shifted, red means red shifted. That just means that the material and the gas that is traced by this blue and red lobe that you see, one is coming toward us, the blue shifted, the red shifted is coming away from us. And this is high velocity gas, so that's the gas which is basically dumped onto the protostar and then ejected at very high velocity along the poles of that protostar. And then when the accretion is finished, when all the mass has been accreted or ejected through the outflows, then you end up with a pre-main sequence star, where often you have a disk around where planets, like our own planetary system, form. Okay? And you can see here, it's an example of, this is an HST, so it's a Hubble image, in the visible, of you have a very young protostar, a pre-main sequence star at the center. Here you see a disk around, and this one is in extension, so you don't, again, the disk is too cold, it doesn't emit in the visible yet, but it absorbs the light from the background. So that's why you see it as a dark feature here. And here's the size of our own solar system. Right? So you can see that they are very comparable in terms of size for that particular object. So this is typically the kind of sequence that we have. A dense crystalline core that starts to collapse from a protostar at the center with outflow, and then as accretion goes on and finishes, then you end up with a pre-main sequence star, and then a normal main sequence star. So now going back to the question that the question I first asked, which was about where does the mass distribution of stars come from? Well, if we now know that stars form in objects like that crystalline core which is shown here, the mass that end up in the star must come from that crystalline core, right? We know that they form in it, the mass collapses, therefore the mass is just from the star is just coming from the transfer of the mass from that core to a protostar. Okay? So now the question is, that's good. So now, what if we try to construct the mass distribution, not of the star anymore, but of their progenitors, of the pre-stellar cores? Do we get the same shape as the mass of the stars? So this has been done in the past 20 years or so, the first study that tried to do that. With Herschel, things have massively improved because of the statistics. This is a Herschel, again, image, so in the far infrared, it's a composite image, that's a different wavelength here. What you see is the blue stuff is just warmer dust. The very red stuff is very cold dust. The reason why it's warmer here is because you have a massive star which is currently forming and which is warming up the dust around it. And where it's very red is because it's very cold and it's just starting forming stars in these regions. And so when you have an image like that, you can try to identify the pre-stellar cores, determine the masses, and plot their mass distribution. So here I just show this image, which is not very nice, which I think illustrates one very important point. Sorry for those that are in the back, it might be a bit low. So this is just a zoom in of that particular region. This is column density, but it doesn't really matter what it is, but basically it shows the structure of the clouds here. And you see these green and white peaks show the location of those pre-stellar cores. The thing is, A star is well defined. It's almost a perfect spherical object that has a clear boundary. But here in clouds like that, that's not the case. Your prestellar core doesn't have a nice clean boundary. It's actually within a much more diffuse cloud, and splitting and defining where the prestellar core finishes and where the rest of the cloud starts is actually very often completely arbitrary. So it's actually something which is not easy to do, and that's why there's a lot of controversy in terms of the result I'm going to show you now, which is the mass distribution of prestellar cores, is because the way these things are identified is not unique, basically. Nevertheless, there's been a lot of research on that topic, and it's quite important, I think, to have a look at that. So now, here what I show you is the mass distribution of the prestellar cores identified in that particular region, which is Aquila. Okay, again, it's the mass along the x-axis, the number of prestellar cores per mass beam, and the blue is the histogram. And the thing that you can already notice straight away is that the shape of it is very, very similar to the shape of the mass distribution of stars, right? The mass distribution of stars is represented with this, there are two different shapes, but it's represented with this dashed line here. So you can see that you could almost make a one-to-one match if you shift that mass distribution of prestellar cores onto the mass of stars. You almost get a perfect match. Right? And so that's led to a number of conclusions. The is that if that's the case, it means that every core that falls in that core mass distribution is a perfect match to one star in the IMF, and that the star formation efficiency, which means that the fraction of the mass of the core that ends up in the star is about 30%. And why is 30%? Is because you need to scale that core mass function, that core mass distribution, by a factor of 0.3 so that it matches the mass distribution of stars. And so when people saw that, it's great. Now we understand where the mass distribution of stars comes from. It just comes from the mass distribution of the cores. But the problem is just pushed another level. Now we need to understand where the mass distribution of cores come from. Right? So it's just pushing the problem further away. Another thing which is important to notice is that in that particular core mass function, the most massive core here is about 10 solar masses, 10 times the mass of the sun. Right? If we say that there's a 30% star formation efficiency, that means that core will form a 3-4 solar mass star. There's no core in there that will form massive stars above 10 solar masses, none. Right? So that doesn't tell us anything about massive star formation. Right? We do not know if it could be just a matter of statistics, right? It could be that if the region was much bigger, this will keep going down and we'll have massive cores. Or it could be that massive stars form in a completely different way. Come back onto this in a moment. So yeah?
Is there a dispute as to how you calibrate those masses? Because it's combined, it's dust grains, and you've got to make assumption about the size distribution within the dust grain to become out with kilograms mass.
Correct.
So that must actually shift. There must be quite an uncertainty.
You are completely right. There's a massive uncertainty of these things.
Well, there you go.
There is a huge amount of percentages. The main one is actually the one that you are mentioning, is the property of dust grains, which we know, I was about to say nothing about, but it's not completely true. We know very little about.
We have the same problem with comets.
Well, yeah. The thing is, as long as you cannot, well, comets is maybe a bit better already, but to be able to, we are basically making a lot of assumptions, a lot of models for this dust grain, just based on what we know, but we don't really, but we don't really know what they are made of. I mean, there are good indications, but unless you could collect these grains and study in the lab, which obviously we cannot do, then we learn a lot. But, yeah, so the main uncertainty is related to the property of these dust grains, that's true. And so the masses can go up and down easily by a factor of 2. That's the typical uncertainty on these things. Herschel, though, is a lot better, because before the Herschel era, before we had that type of maps, we had maps where we just had one wavelength, and for which we also had to assume the temperature of the dust, in addition to the dust properties. We have also to assume the dust. Here, with this type of images, we can actually derive what the dust temperature is. So it's an improvement, but there are still a lot of uncertainty. Yes, that's correct. So now, the question becomes, as I said before, we have now the core mass function that looks like the mass stellar mass distribution, but we still don't understand, therefore, what shapes the mass distribution of cores. So it turns out that cores mostly forms in filaments, right? So, and that's really a result from the Herschel studies. I'm not sure what this says. So here, what we see on this image is a torus molecular cloud again, torus star-forming region. The red symbol that you see here shows the position of a prestellar core or protostellar core. So it's basically a piece of dense gas which is currently forming stars or will form stars very, very soon. And then you see these shaded gray things are filaments that have been identified in the region. How dark these filaments are shows you how unstable they are against gravity. What I mean by that is that if you have a light gray filament, this filament is very unlikely, the cell gravity of this filament is very unlikely to fragment it into cores. If it's dark gray or black, it means that this filament is very likely to fragment into cores due to its property. Property, I mean its mass and its temperature, basically. And so we can see that the red symbols are almost systematically located on top of these unstable filaments. So that means there is a link between filament properties and core formation. In fact, what dictates the formation of cores are the initial condition of the gas and the dust inside those filaments. How am I doing with time? I have no idea. 20?
20.
Oh, excellent.
Or a bit less if you want to have some more questions.
Okay, that's fine. I'm good. So yes, so filaments, the cores form inside the filaments. That's another region, which is IC5146. Again, that's a Herschel image in the 5 farad. That shows you the colors are slightly different because it is made by a different person. That's all what it means, the colors here. But the red is again a bit warmer. You have a massive star forming here, and then the orange stuff is called dust. And you see a lot of filaments. Filaments have been identified in that region, and then what this team of people has done is to plot the width of these filaments. Why not? And the width, it turns out, is very, very uniform. So here's the width of the filaments, how broad they are. This is the numbers, again, that's the orange histogram. And you can see there's a clear peak at around 0.1 parsec. Right? And this was completely unexpected. Right? When people have seen that, what's going on? Because normally, what you would expect to see with normal pure gravity and thermal support kind of physics, you would expect to have a broad range of filament width, but we don't see that. And what has been proposed is that maybe that means that these filaments that we see in this image are being formed through the compression of what we call turbulent shock. In the interstellar medium, you have a lot of kinetic energy that drive motions, chaotic motions into the gas, and then you have this bubble of gas that start to hit each other, that compresses the gas, and that compression may form filaments. And we expect, if that happens, we expect that the width of this filament formed in that way to have a width of 0.1 parsec. So that could be evidence that these structures are directly the product of turbulent shock in the general interstellar medium. So now, so just to show you, maybe to illustrate a bit more what that turbulence is, you have a small movie, because turbulence is not necessarily something that we come across often, but I mean, in real life we come across very often. But anyway, so here's a simulation where you have some gas in that simulation, you inject energy, and because it's a very high, what we call Reynolds numbers, it doesn't really matter, but the gas just very quickly the motion of the gas becomes quickly chaotic. The yellow bits shows the denser bits in that simulation. You can see there's a lot of motions, a lot of filamentary structure that are being formed. If you look at the width of this filamentary structure in that simulation, you see that they are close to 0.1 parsec. And so that could be the trigger for the formation of these filaments. So now scenario for the formation of low mass stars and stars like the Sun, with the formation of filaments through turbulence, then only the densest, that turbulence would form low density and high density filaments. The high density filaments will become unstable due to their self-gravity, start to fragment into cores, the cores form stars, done. Star formation is solved. Great. And so that's what I would say most people think how these low mass stars are formed. Right? There's still a lot of controversy. This scenario doesn't fit all the observations, by no means, but that's what came up in the past, I would say, 10 years. Now the issue is that that scenario cannot explain massive star formation at all. The reason why it cannot explain massive star formation at all is because in that filament that we have, 0.1 parsec width filaments, the temperature of these filaments and their densities are such that they will fragment into 1 solar, 2 solar masses cores. They cannot fragment into 100 solar mass cores. It's just not possible. The physics tells us it's not possible. Right? That's called something that's called the Jeans mass. I don't know if someone, it's a technical term, but basically it gives you, given the density and the temperature of that filament, it tells you what's going to be the mass of the core that will fragment from that filament. And this is about a solar mass. Right? So if you want to form a 10 solar mass star, or even a 100 solar mass star, right, you will need that core to be at least 100 solar masses itself, and probably more than that. So we know that they cannot form through that way. Another issue with massive star formation is that, as I said before, in that particular mass distribution of cores, here the most massive one is 10 solar mass. That's true for that particular region, but so far, we haven't found really a massive prestellar core which is 100 solar masses. We search a lot, and I'm going to show that now. So all the results that I showed you before, right? Everything I told you is located, all the regions that I showed you are located within that tiny white circle there. So this is not our own galaxy, because we don't take a picture like that. But if the galactic center is here, the Sun is roughly at 8 kiloparsec from the galactic center. Thus, all the star forming regions I showed you are located within that tiny white circle. Right? And so we are extrapolating what we learn from this region to the entire galaxy that we see there. Right? So is that really, can we really do that? Some people will say yes, we can. Some others will no, we can't. Well, now what we need to do is to look at how star formation looks like in other regions across the galaxy. The issue with that is that they are further away, so you need telescopes that are able to resolve the star formation better. You need instruments that provide the amount of details that we need so that we can actually study them. So here it's, so as I said, no massive prestellar cores have been found. And so the first thing that people try to do is to go further away in the galaxy to try to find this massive 100 solar masses prestellar core. And there have been some very good candidates for that. So on the left here, what you see, it's 3 different sources seen. So this is the mid-infrared, so they are seen in extension. Again, you have very cold dust absorbing the light in the background, the greenish stuff. And this is true for 24 micron as well, and 70 micron as well. It's dark, it's blue, it's absorbing the light from the background. So that was a very good indication that there was no stars in them. But these regions are located, 5 kiloparsec away from us, compared to 200 parsec away from the region that I showed you before. So they are 20 times further away in the galaxy than the region that we studied before. Still, with the sensitivity of the data that we have and so on, we see that there are a series of objects that are completely starless, at least they look starless. And this is the same object at 350 microns, so they emit now because they probe cold dust. So these objects are massive, they are cold, and they seem to have no protostars in them. Now when we look at this object with ALMA, which is a very, very powerful, the most powerful millimeter telescopes or series of telescopes in the world, you see these things. So these are basically the zoom in at with very high resolution. And you see that all these objects now fragments into smaller bits. More than that, all of these fragments have very complicated blue shifted, red shifted emission tracing outflows, right? Here, the detail of it doesn't matter. What it shows here is that you have a lot of outflows. When we see outflows, it means you don't have prestellar cores anymore, it means you have protostellar cores. You have already a protostar that has formed at the center. So these objects, in the end, when you see them at the same kind of details as those regions nearby that you can see, then they are not massive prestellar cores anymore. They only have low mass protostars in them. So we cannot find these massive prestellar cores. And they've been searched for across the entire galaxy now. So we know they do not exist. There may be one or two examples that could be, but the vast majority, it's a no-no. So how do massive stars form then? Right? Now we know that that picture of a massive prestellar core that will just generate the formation of a star at its center through the accretion of the envelope onto the protostar just does not work. So now we have that type of observation. So what you have here is what we call an infrared dark cloud. So again, you see you have the background light in red, and then you see you have these dark filaments that you see, which again is called dust absorbing the background light. You know all about that. And at the center here you have this greenish emission that shows a high mass photostar. In fact, when you observe this with ALMA, again, the same interferometer I showed you before, what you find is that you have a core here, which is in fact one of the most massive protostellar cores, so there's a protostar inside, ever observed in the Milky Way. It has 500 solar masses of gas within a very compact region. And so now it's very troubling because you need to understand how is it possible that so much mass is being packed up into such a small volume. And clearly that's a very good condition for forming massive stars, but we still don't understand how that comes about. The reason and how that comes about is because it's given, the clue is given in these filaments here. They're all pointing towards that object. Right? The reason why they're all pointing towards that object is because everything is collapsing and feeding that protostar. The full cloud, now it's just about the small tiny core we are talking about. This is the entire cloud, which is so massive and so dense that it's fully collapsing toward its center of mass, where the most massive stars form. So now we don't have a nice single prestellar core that's collapsing and forming a massive star. What we have is probably it starts with a small, low mass prestellar core that starts collapsing, but at the same time it collapses and starts to form a star, it accretes a huge amount of mass to the collapse of its own cloud. So massive star formation is a lot more dynamic. In fact, here on the right, you have a velocity map. So that what shows is the motion of the gas. So far I insisted on dust, but in fact in the star forming region, the mass is completely dominated by the gas, not the dust. The dust is very useful to trace star formation, but most of the mass is in the gas. And here it's, with the gas you can get velocity. And so that shows the blue shifted and red shifted that come together toward the center, and it's very messy. But that's how we think this very massive star form. Here we think typically that at the center of that object, something like 100 solar mass star is currently forming. 100 times more massive than the sun. Okay, I'll finish quickly. So now the thing is, if we know that some clouds collapse and form massive stars, how common is that collapse and how extended the collapse is? So I said just before, I said the entire cloud is collapsing, but is it really the entire cloud that can be, 100 parsec, 1 million solar masses? Is it the full thing, or is it just a fraction of it, or what it is? So the structure is a structure we try to look at, and so here is what we call a giant molecular cloud. So it's a giant massive star forming region. The mass of this thing, as I just said, is 1 million solar masses that you have in that cloud. You have different contours. You don't really care about the contours, but what it shows is that it gets increasingly denser and denser at the center here, where you have a similar cloud as the one I showed you before, right, that formed a very massive star at the center. And now what we want to see is only the central bit collapsing, or is it the full thing collapsing towards clouds? And we've done that for a number of clouds, looking at some plot that's becoming a bit more sciencey, but it doesn't really matter. That is the radius of the cloud. So we look at different radii within the cloud itself, and we look at the gas velocity dispersion. It's just a way to see if the kinematic of the gas changes as we go in radius. If the full cloud is collapsing, we don't expect to see much changes as the radius becomes bigger. If it's just a small part, a fraction of the cloud which is collapsing, we do expect to see a change in the slope. And for some clouds, we do. So if you look at this, that's the central part of the cloud. This is the outer part. And this line shows the velocity dispersion. And so we see that at the center, it has a certain behavior, and then it decreases toward the edges. We believe that's an indication that at least the central part of that cloud is collapsing. 80% of the cloud, roughly, that we studied, seem to have that behavior. So that would mean that in that particular case, it's not the entire cloud which is collapsing toward this. It's probably just that bit here, which is already maybe 10,000 solar masses worth of gas collapsing towards here where massive cloud is forming. So here we are not, low mass stars formation is really looking at the cores and how this cores collapses on very small scales. Massive star formation involves a huge amount, a huge fraction of the parent star forming region. Okay, I'll skip that and I'll just go here, which is about now scenarios for massive star formation. So here I gave you my view on massive star formation. I do believe, and I think we have the evidence that massive star formation is very dynamic, that it involves the collapse of a huge fraction of molecular clouds, and that's the only way you can pour so much mass into such small volume. But you can see here are 3 different sketches from 3 different papers in the very recent literature in the past 5 years, showing similar kind of scenario for massive star formation, but with profound differences in the physics that govern the evolution of this. And so this is just to show you that there's still, even though I presented you confidently a set of results in which I'm very much involved in, so that's why my biases come in, there are still a lot of debates whether, how really high is the and with that, I'll stop it, and thank you.
Thank you very much, Nicolas, for getting us off to an excellent start and a very clear explanation.
Good, I'm happy.
Of your subject. Those outflows from forming protostars or stellar cores, are those driven basically by rotation? It's by the conservation of angular momentum?
That's exactly that, yeah. So one big issue in star formation is that if you take the angular momentum of the core in which the stars form, then the star should not be forming at all, because there's so much angular momentum that should create a disk that is fully stable and never collapses towards the point. So you should never be able to form any star at all. So you need to get rid of the angular momentum, and we believe that the way that the gas manages to get rid of the angular momentum is through the outflow. The gas basically is being at the same time is slowly contracting, is being entrained by the magnetic field in a loop along the pole and generating these outflows. Yeah. Mm. So that's a way to get rid of the angular momentum, which if you don't, you just cannot form these stars.
We do actually see those in our amateur observations sometimes. We have things called variable nebulae,
yeah,
which we've got some people in the BAA studying, and these tend to be these cone-shaped structures, yeah, coming out in one direction, because you usually only see one direction. You don't see the one away from
you.
Because
they are probably more evolved. So the thing is, what you see, most of the thing that you see is in these outflows is the gas which is being entrained by a central jet. Yes. And so depending on the distribution of the gas around your protostar, you might see one lobe or two. So at early stages, very often we see 2 lobes because they are deeply embedded into a dense envelope of gas, and therefore the gas is being entrained in both directions. But when it's more evolved, the distribution of the gas might be a bit more sparse, and therefore you might just see only one lobe.
Yeah, the most famous one is Hubble's variable nebula in Monoceros.
Yeah,
that's
Monoceros. My PhD study was Monoceros.
That's right, yes. So, are there any other questions? Let's have the gentleman at the back left here.
Yes, just maybe a couple of questions. Firstly,
we've only got time for one.
If there is a different methods of medium mass stars and high mass stars being formed,
yeah,
wouldn't you expect some sort of discontinuity in the initial mass function to appear?
That's an excellent question. The answer is yes, you would. But my view on this is that it's not one or the other. So basically, if if you go back to what these scenarios really are, for low mass stars, we are saying most of the stars coming from a tiny core. For massive stars, and most of the mass is coming from the larger scale accretion. But probably, in fact, you have a continuity of these two processes happening at the same time. And the mass of the star is just a reflection of how much mass is coming from the core of the larger. So yes, exactly. I think it's a total overlap. You go from 100% core accretion for low mass stars, probably to 100% cloud accretion from for massive stars, and everything which is in between, you have a varying fraction of these two things.
Yeah, I'll take a few more questions because I don't think we need quite so much time. For refreshments has been timetabled. This gentleman in the front.
What you talked about so far is mainly based on information coming from our own galaxy. And that with an interstellar medium or with all this gas coming from outflows from population 2 stars and population 1 stars. What do we know about the very early universe? The formation of, yes.
So observationally, nothing, right? Because at the moment we cannot observe them. But there's a lot of theoretical work on them. So the idea, the main idea is that when you are very early in the universe, the metallicity of the gas is completely different. So you basically have no metals. Metals meaning heavy elements, are very useful in the physics and the chemistry of the ASM, especially it allows to cool the gas efficiently through light emission. If you don't have that, the gas cannot cool as efficiently. If the gas cannot cool as efficiently, you have a larger Jeans mass, so it means that the gas fragments on much larger scale, and so you tend to form more massive stars. That's why it's been widely believed that in population 3 stars, in the very early universe, these clouds form a larger fraction of very, very massive stars. But here we are not talking about even 100 solar mass stars, we are talking about 1,000 solar mass stars. So very massive stars. So that's what we believe. But it's only based on numerical simulations. There's no observational evidence of that.
Lady at the back.
Yeah, you show computer simulations of turbulence linked to filamentation. Are there any, however simple, analytical models to explain the physics of that?
Yes, there are quite a few. So filament studies really developed with Herschel, because before that we didn't have the sensitivity to see many of these filaments. Since then, so in the past 10 years, a lot of literature has been produced on filaments and filament fragmentation. Even before then, there was a lot of theoretical paper trying to understand. So I said, for instance, that we have these filaments and they fragment into cores. There's a lot of 1960s papers, a lot like maybe 5 or 10 1960s papers looking at the fragmentation of cylinders on an analytical perspective. And they do predict constant separation. So the thing is, they're always in ideal situation, right? That's the problem with these analytical papers, and that's why I haven't talked too much about them, is because for the purpose of their work, they need to have very simple solutions. So they start with infinite cylinders, for instance, that are perfect cylinders, and in this kind of, with uniform temperature, and if you are in this condition, you can predict that the cores will fragment with regular spacing between them, and so on and so on. So you do have a number of papers you can refer to, but the reality of things is that it's a lot more complex than that. And so analytical studies have strong limitations with respect to star formation because of the complexity.
Yes.
I'm not sure if this question will mean anything, but at what point, when the cloud's collapsing, does nuclear fusion start?
So nuclear fusion only starts when you reach the center. The central temperature is about the order of 1 million degrees Kelvin at the center. You don't start that before. And that's really only, so the time at which hydrogen is being burned into helium is by definition when the star enters the main sequence. And so that's really at the very, and when all the accretion is done, basically. This is true for low mass stars. For high mass stars, they start in fact burning hydrogen into helium before they finished accreting. And that was one of the arguments in the 1980s to say that people wouldn't understand at all how massive stars form, because as soon as the nuclear reaction starts to occur, your object becomes extremely bright. It becomes so bright, in fact, that for a 10 solar mass star, it should stop any further accretion. the radiation pushes away the gas very efficiently. So you should not observe stars that are beyond 10 solar masses. And the answer to that question that they puzzled researchers for at least 20 years was the fact that the accretion does not occur in a spherical way. It occurs through a disk. And so most of the radiation can actually escape, and still it can increase through an equatorial disk, basically. So that's how the issue has been solved.
We'll have just one more question. This gentleman in the red.
Yeah. Your results and the mass distribution,
Yeah.
you say that's from our locality within the galaxy.
Yeah.
Have we had any chance to look at either the core of the galaxy or the halo?
Yeah, that's another good question. So ALMA, this instrumental that I mentioned, it's been around now for 10 years. So it opened in first observation in 2011. That was a real game changer because before then, everything was beyond that white circle that I showed. We didn't have the angular resolution to see the cores. Since then, it's not in a statistical way. Since then, we are able to do that. So people have done it in further away regions. What they find when they compute the same kind of distribution of the cores is that it doesn't look the same. It's actually flatter. So they have a higher proportion of massive cores. But me personally, that's my own view now. I am very skeptical of these results because there are many biases that come in the observation themselves and the way they are being treated. Observing with a single dish, a single telescope, nearby region, and observing far away region with an interferometer introduces a lot of differences in the type of images that we get that might result in the difference in the shape of the coma function that we get. But if you believe these papers, what they are saying is that the coma distribution don't look the same everywhere in all stars. But then the question is, how come then the mass distribution of stars does? And invite me again in 10 years.
Well, we might well do that. So it's very pleasing you've all got so many questions. You're all really following this very intelligently. So, and we'll have much more along similar lines later on today. So if anything that hasn't been asked so far, it'll probably still be relevant later. We'll thank Dr. Nicolas Peretto once more for coming and giving us all the latest information. The tea and coffee break now will last until 12 o'clock. Take your seats, ladies and gentlemen, please. I hope you had a nice refreshments, nice chat. So at the beginning, I didn't say very much about the BAA. We talked mainly about the Cardiff Astronomical Society. I'm the president, as I said. We are the National Astronomy Society, mainly for amateur astronomers. We do have some professionals in our ranks as well. The BAA is formed in 1890, and we specialise in observing everything that we can in the sky and educating amateur observers and getting them to a higher level of observational expertise, encouraging observing at all levels, from beginner to collaborations with professionals. We have observing sections with each led by an experienced director who's an expert in a particular subject, whether it's the sun or one of the planets or variable stars or aurorae, whatever, and whatever area of astronomy you're interested in, whatever area of observing you're interested in, we can give you good advice to get you going and improve your skills. And we hold meetings all over the country. Most of our meetings are in London at the Institute of Physics, but we have 2 or 3 meetings at least in different parts of the country every year. Our forthcoming meetings, the next one is historical section meeting. That's 20th of May in Birmingham. And you can find all these meetings on our website on britastro.org. And you can book up for them. So that's another all-day Saturday meeting on the 20th of May on history in Birmingham. Then 7th of June, that is a Wednesday. That'll be a London evening meeting on the 7th of June at the Institute of Physics, when we have our George Alcock Memorial Lecture, which we have every year. And that's that's the last meeting we have in the Institute of Physics for until the autumn. And then there's another Saturday meeting on the 8th of July in Greenwich, which will be a meeting of the comet section of the BAA. So if you're interested in those little fairy bodies, they will, which are not cats, but the comets with tails or without tails, that should be a fun thing. If you're not a member of the BAA, you can find out more about us on our website or by speaking to me or other BAA members here today. And if you're at all interested in contributing to observing at any level, very much encourage you to join. You can join as a full member to a paper member to get the journal sent to you every 2 months and our handbook as well annually, or you can be an online member and get the journal by just by email, and that's cheaper. You can. I encourage you all to join if you're not already a member, or join your local astronomical society if you're not a member of that as well. So our next speaker, it so happens that I met him quite recently, actually, at a very swish event in London at the German ambassador's residence, when a medal, which was called the Caroline Herschel Medal, was being awarded to a lady who developed the near infrared spectrometer on the James Webb Space Telescope, which has been such a huge success and such a huge hit recently. And that medal is specifically given to women in astronomy for a lifetime's achievement. And it was jointly organised or funded by the Royal Astronomical Society and the German Astronomical Society. So that's why it was at the German embassy, and we were able to meet some of our German astronomical counterparts. And it so happened that Professor Mark Birkinshaw was there, but he are you at the Cardiff University?
No, I'm at Bristol and at Cardiff.
Right.
A short
I only have to be there a small fraction of the time.
Right, well, Professor Birkinshaw works with radio, optical and X-ray telescopes, and he studies galactic nuclei and radio sources, and he's been interested in the theory of how relativistic outflows remain stable and emit radiation in all wave bands. He has worked on the effects that massive objects and their atmospheres can have on the microwave background radiation, and he's made measurements of shadows cast by clusters of galaxies. I've never heard of that before. And today he is going to talk to us for nearly an hour about supermassive black holes and their effects on their surroundings. So please welcome Professor Mark Birkinshaw.
Okay, well, I'll try to hold it down to about an hour. Once I get the podium, there's no saying how long I'll go on. So this is a topic that I was assigned by Hazel back there, so I hope I do it appropriate justice. So my main title is Supermassive Black Holes and Their Effects on Their Surroundings. And as a subtitle, how about, do we need to worry about the beast at the centre of the Milky Way? And no spoilers. You'll find out as we go through. So let me start by just showing a couple of red images of a couple of rather well-known NGC elliptical galaxies. On the left is one of my personal favourites, NGC 6251, and on the right is one of my personal bugbears, NGC 1700. I think you will agree that looking at those images tells you essentially nothing about anything very exciting going on. They're just the usual elliptical blobs that elliptical galaxies tend to be. On the left, maybe you can see at the top of the screen that there's a spiral galaxy that is perhaps a little bit too close to its friend at the bottom. But that's really all we can say about that. And here's a couple of spiral galaxies. On the left, we have NGC 4051. Some of you may recognise the name. And on the right, NGC 4278, that I'm sure some of you have observed since it lies in the Virgo cluster. And on the right, you'll see that it's got a friend on the left with which it has been interacting. The left-hand galaxy is very active. The one on the right is not so active. And again, it's a bit hard to tell, based on these images, whether one is going to be particularly exciting or just the usual dull galaxy. I say that with some regret, since your previous talk was about star formation. Now, although this sort of image doesn't really give very much away about what's going on, if you look a little bit closer, you can often see that something interesting is happening. And an indication of that is whether the central region of the galaxy is just smoothly becoming brighter than the region around it, or is unusually bright. And here's NGC 4051 again, in a slightly different grayscale representation. I think you can see that the core of the galaxy is really quite small. And indeed, the image that we're looking at here is comparable in size to a star image over here on the right. If this core was as bright as the nearby star, I assure you would see diffraction spikes in the same way as you do down on the right. That is, a lot of light is concentrated into a very small volume towards the centre of this galaxy. This thing's a so-called Seyfert 2 galaxy. Okay, let me just start to set out some scales. How bright are galaxies in general? Well, let's take our galaxy as a template. It's about 2 × 10⁻⁻10 solar luminosities in brightness. That is about the same amount of light as 20 billion suns, ordinary suns. And most of that luminosity is in starlight. Well, starlight and infrared light, which is re-radiated by dust, which has been heated by starlight. So indirect starlight, if you like. Now, for Seyfert nuclei, only a small fraction of the light sometimes comes from stars. And we're seeing a large fraction of the overall light of the galaxy concentrated in a small nucleus. We know that it's not all starlight because the spectra that we see are definitely not starlight. This is another Seyfert galaxy. This is actually a Seyfert class 1 galaxy. I chose that because it's much more spectacular. What you can see is very strong emission lines of hydrogen, a little bit of nitrogen there, oxygen, another bit of hydrogen, hydrogen and some more oxygen, and so on. Notice these lines are very broad. That is, rather than having the narrow emission lines that you normally get from gas in a galaxy, we're seeing emission lines that are, well, in that case, hundreds of angstroms, many tens of nanometers wide. When you get very broad lines in pretty much any astronomical situation, you immediately know that you've got a Doppler shift going on. And to get a 100 nanometer wide line at, say, 5,000 nanometers, the gas has to be traveling at 100 divided by 5,000 times the speed of light. So the gas that we're looking at here that's emitting those lines is travelling at thousands of kilometres per second relative to the central velocity of the overall galaxy. Now, if we had a star in that region that was travelling at 1,000 kilometres per second, it would escape from the galaxy, because the escape speeds from these galaxies are of order, well, usually 300 kilometres per second, 400 kilometres per second. So these stars would be gone. And any gas that's there, unless it feels resistance, would also be gone. So if the gas is moving this fast and isn't gone, it's being held in by strong gravitation of some kind. And strong gravitation and a star-like core, a very small volume in which we're seeing the emission, implies a lot of gravity, and the most likely culprit to produce that lot of gravity is a supermassive black hole. Now, I'll justify that over much of the rest of the talk, because otherwise it's a big jump, but justify it I will. I should say, by the way, that people thought these things were supermassive black holes even before the evidence was any good. There's a certain theoretical bias in the community, fortunately. So let's ask, what do supermassive black holes do to their immediate surroundings? After all, that's part of my talk, part of the title I was given. Well, the first thing they do, if you've got a very big vacuum cleaner sitting in the middle of a galaxy, is it will hoover up anything that gets too close. And a very good example of that is something that was announced on the BBC News yesterday. That's this transient source, AT2021 LWX. This is a galaxy at about a redshift of 0.88, I think, which suddenly got bright. It suddenly got bright, and it has stayed bright for a ridiculously long amount of time. So something has suddenly, I'll come around this side so I can point, caused it to go from 24th magnitude up to 20th magnitude, brightened by more than a factor of 10 over a period of some 100 days. It's now staying bright but gradually declining. It's as if something has suddenly shoveled a lot of mass down onto an object that wants to become bright, if it can make it, and it's still feeding off that mass. The luminosity of that burst, around 2 times 10 to the 12 solar luminosities. That's much larger than the luminosity change you get if you normally take a star and throw it at a black hole. You throw a star at a black hole, it'll just eat it, and it'll be there and gone, and you'll get a burst that's maybe 10 to the 3 times fainter. Well, what else will a supermassive black hole do? Well, it's got strong gravity. As you take a planet in our solar system and move it closer to the sun, it moves faster. The same thing happens in this situation. Near a larger mass, as you get closer, you start to move faster. And a lovely example of that is this movie, which I hope plays, which shows the stars in motion around the supermassive black hole in our galaxy's centre. You can see that as they get close to the supermassive black hole, which is marked by the star, they turn very suddenly in their orbits. That is, they're getting close to their periastrons, their closest points of closest approach, feeling a lot of acceleration. The star, which is highlighted in yellow there, known as S2, gets extraordinarily close to our central black hole in the galaxy, and at its peak speed, it's travelling at 1/40th the speed of light, which is a good deal faster than we can get any rocket to go at. So a natural phenomenon is quite happy to take an entire star and move it at a 40th the speed of light. Although the orbit that you can see there looks elliptical, looks like it closes in the usual Newtonian sense, it actually doesn't. In general relativity, if you put a very large mass into space-time, it makes space-time distort. And it distorts in such a way that the ratio of distance from the center to circumference, so if you like, circumference divided by radius, which for a circle is normally 2 pi, becomes a different number. And that means that as this object goes round, it loses a bit of angle every time it goes round. We say there's an angle deficit. And the orbit gradually turns, it precesses, in the same way that the orbit of Mercury precesses around the Sun. Well, not quite the same way, because the orbit of Mercury around the Sun precesses very fast. It's almost a degree a year, a degree a century, rather. But within that, there's a 43 arcsecond per century general relativistic term. This star is getting so close to the black hole that it's also precessing, but at a somewhat faster rate. As you can see, another star there, the one that comes in from upper left and then goes back out almost parallel, also has very strong acceleration near the black hole. But unfortunately, its orbit is so long, it's going so far out, that it'll be a very long time till it comes back and we get a chance to see whether its orbit has also precessed. That's the motion of stars. We can also talk about the motion of gas. Here's another of the most prominent nearby supermassive black holes. This is in the galaxy M87 in the Virgo cluster. And what I'm showing you here is on the left, on the lower left, a picture of the hydrogen alpha emission from the galaxy. That is warm gas that's held near the core. And on the upper right, the motions of that gas as a function of position across the slit that's shown in the black outline. You can see that as you get closer to the center, the speed goes up, it goes through a zero, goes back down, goes out again. That extra velocity gives you a measure of the mass of the thing that's doing the accelerating. Just as here, the speeds of the stars give you a measure of the mass of the thing that's doing the accelerating. And the mass of the thing that's doing the accelerating, in this case, is about 6 billion solar masses. For our galaxy, it was a mere wimpy half a million. This thing is more than 1,000 times more massive. Okay, what else do black holes do? Well, if they're rotating, they don't just provide strong gravity, but they drag space-time around with them. So anything that's trying to orbit in a nice, respectable plane will find itself being pulled all the way out of shape as the positions it's trying to move in get taken away from it. And here's a simulation that I stole from Simon Tiran in Vienna, showing the motion of an orbiting particle in a rotating black hole. This is describing the equivalent of a Newtonian orbit. I think you can see that it's just a little bit pulled out of shape. So that rotation provides an extra source of energy, by the way, that can be tapped into for affecting material near the black hole. Okay, what else do black holes do? Well, they do a lot. But another useful thing to remember is that if you're trying to throw stuff into a black hole, unless you're very accurate and going right along a line of radius, you're going to throw stuff in with some angular momentum. It's going to want to go around rather than in. And if it's gas, it's going to hit other gas and want to settle down into a rotating disk. So around any black hole that is currently feeding, you expect a disk of material that has sort of settled into an equatorial plane, defined by the average angular momentum of stuff that wants to go in, with some caveats, but I'll just ignore those for the moment, that will just sort of sit there, except that orbits aren't always at the same precise velocity. There's a differential rotation. So gas at different distances from the centre drags other gas. And that causes gas that's closer to the centre to want to lose momentum and to drop in, and gas that's further out to go out. That's an accretion disk. Normally when we see accretion disks, like around forming stars, we see nice emission lines in the optical, in the infrared. For supermassive black holes, there's so much more mass, there's so much more friction, there's so much more heating. You don't see the lines in the optical, you see them in the X-ray, because the gas is that much hotter. And because you're in the neighbourhood of a lot of mass, as the light that's being emitted from the accretion disk tries to come out from the mass, it gets redshifted. So what we tend to see are lines of very ionized iron in the X-ray at about 6.4 kiloelectron volts. But those lines are not symmetrical. And they're not symmetrical because of the relativistic effects of being so close to a supermassive black hole. The specific thing I'd point out is this long red tail, the tail to lower energies beside the peak. And that is a signature of a rotating black hole and you being rather close to it. The amount of the emission line that is in that tail tells you something about how fast the black hole is rotating. Why is that? Well, if you've got a static black hole, it has a thing called an event horizon, the thou shalt not pass out surface, which is 2 gm over c squared away from the centre. And I use the word away here in rather approximate terms. But there is an event horizon. If the object is rotating, that shrinks. And an accretion disk can get closer to the mass before it starts to break up. And that means the light gets more redshifted. So 6 keV photons become 5 keV, become 4 keV. The faster the rotation, the longer the tail, and the more emission line that is in it. So the asymmetry here tells you something about rotation, and also if you've got an accretion disk, some of it's coming towards you, some of it's going away from you. There's also a Doppler boosting thing to worry about. So the Doppler effect comes into play. So this again is an indicator that there is a supermassive black hole in a typical Seyfert galaxy or NELG narrow emission line galaxy. What else does these supermassive black holes do? Well, along with any other sort of mass, they bend light. And the most spectacular example of that would be the famous ring, sometimes called a shadow of a black hole, in M87. It was published by the Event Horizon Telescope collaboration a few years ago. This was called the image of a 6 billion solar mass black hole. What we're seeing is photons that are getting close to the event horizon that are being bent around and are piling up at the edge where, I use the technical expression, phase space gets concentrated. Basically, photons like to be in that sort of location and you get more of them. So you get a bright rim which is not precisely at the event horizon, but a bit further out. But the scale of this is that 6 times 10 to the 9 solar masses has to be concentrated within the scale of the solar system. So a lot of mass is very concentrated. And the only object we know about that can do that is a supermassive black hole. And finally, and perhaps paradoxically, these supermassive black holes, the ultimate vacuum cleaners, not only absorb but also send out. They're very messy eaters, if you like. As they try to consume some material drops in, because of drag on adjacent material, crudely, they throw out a large fraction of what wants to go in. And a schematic of what's going on, incorporating some of the things that I've spoken about so far, is shown here in this diagram, which is, I stole it from part of a plea to a funding agency to produce a new X-ray telescope. That telescope is being built and, as usual, is well over budget. What do we have here? Well, the black spot is obviously the black hole. And around it, top and bottom, is the accretion disk of material that is gradually being fed in from the side. Very close to that central region, we have other clouds of material that are moving around very fast because they're close to the mass. And those clouds produce the broad emission lines that I showed you in the spectrum of that Cepheid-1 galaxy. Further out, there are other clouds. The whole environment is going to be pretty messy. But since they're further out, they're moving more slowly, and they produce the narrow emission lines. So we talk about a narrow line region and a broad line region. I should explain that the scale along the bottom is in gravitational radii. And rule of thumb for gravitational radius, a 1 solar mass object has a gravitational radius of 1.5 kilometers. And you can just simply scale everything. So for a galaxy like M87, where the mass is 6 times 10 to the 9 solar masses, 1 RG is 10 to the 10 kilometers. So we're looking at a scale from about 10 to the 11 kilometers to about 10 to the 17 kilometers. That is a scale from comfortably within Mercury's orbit out to a parsec. Now, not only do you have these line-emitting clouds, but also you can get a directed jet-like outflow, which is produced by material that is being accelerated by a combination of gas pressure from the upper surface of the accretion disk, which tends to get quite hot, and wrapped up magnetic field that is tied to the accretion disk. It is a feature of astrophysics that magnetic fields get stuck, and they get stuck in specific lumps of matter. If the matter wants to rotate, then they drag the magnetic field around with them. And so if I start with some magnetic field that's sitting nicely up and down and start turning it around, it's like winding up a whole set of elastic bands and making a very tight funnel. Material can then flow up. The way that a physicist would describe it is that the magnetic field becomes strong and it drives a Poynting flux-driven jet. That is, electromagnetic radiation pushes on the matter and causes it to go out quite fast. And when I say quite fast, superluminal knots, we see things moving out at 10, 15 times the speed of light. They're not actually moving at 10 or 15 times the speed of light. They seem to be moving that fast because these flows are brightest when they're pointed towards us, and then there are geometry effects that come into play. But to be superluminal, to be seen to be superluminal, we know they're travelling at a good fraction of the speed of light. And by good fraction, I mean 98%, 97%, something like that. You know, they're getting a move on. Now, in this diagram, this shaded bit, this outflow, is rare. We see it in only about 5% of all active nuclei. So the radio outflow is a rare phenomenon, where the emission lines, the narrow emission lines, certainly are a fairly common phenomenon. So there's some sort of duty cycle involved. There's some sort of process which says this black hole is going to go bright now, and this black hole ain't. And that's going to be something to do with how well fed it's getting. Here's a picture showing what a black hole could do to its environment. This is a picture of a numerical simulation, quite an old one now, after, on the left, about 10 megayears, on the right, about 20 megayears after the feeding of the black hole has turned on. And what's happened is that as this black hole has rotated, it has driven those up and down, which are of very low density, but very fast moving. And as it's done that, it's made the gas around it swirl around and settle into a disk of high density where stars can form. So not only do we get a very fast outflow, we have sort of paradoxically created a sort of slow-moving pool of denser gas which can start to make stars. So when you see an active galactic nucleus, you quite often get a combination of star formation and this jet-type activity. Let me go back to M87, one of my favourites. This is an X-ray picture taken with the Chandra satellite, which I helped build. What you're seeing here is X-ray emission from hot gas in the neighbourhood of the galaxy. The galaxy itself, since this is a giant elliptical galaxy, would fill that frame. So we're looking at the brightest X-rays in the middle. And I think you can see that the gas is looking very chewed up. It's not a nice smooth ball. It's got all sorts of bits and pieces. If we expand the centre, you can see the jet in X-rays coming out of the central region. And beware, by the way, that black spot at the centre that looks like it might be a black hole is in fact a black hole, but the black spot is because it's so bright it overloads the camera and it causes all the numbers to be reset to 0. So we can't see that bit in this particular image. You've got to drive the camera in a different way to make that work. I can be more technical with people who are interested. Now, although active nuclei, the type I'm sort of fond of, are sort of rare, to the best of our knowledge, every pretty-looking galaxy has a central supermassive black hole. Every pretty-looking galaxy, every elliptical, every nice spiral. And, strange fact, the mass of the central supermassive black hole is about 1 part in 1,000 of the mass of the spherical assembly of stars, or spheroidal assembly of stars, near that black hole. So in a galaxy like M87, where you've got 6 times 10 to the 9 solar mass black hole, you've got a 6 times 10 to the 12 solar mass galaxy. In our galaxy, where it's about 500,000 solar mass black hole, you've got about 500 million solar masses of mass in the sphere part of the galaxy, the bulge. The disk is irrelevant here, it's too far out, it doesn't affect things. But the bulge is what matters. Here's the plot from Herring and Rix in 2004, which relates bulge mass and black hole mass for about 30 objects. You can see there's quite a nice correlation. This has been done with many more objects using other sorts of indicators, and this relationship seems to hold up in a remarkably good fashion. Now that's an interesting little paradox, because a supermassive black hole is still smaller than the solar system. A galaxy like M87 is 100 kiloparsecs across. So how does 100 kiloparsecs of galaxy know to conspire with a central black hole that's only one solar system scale in the middle? There's got to be some sort of collaborative process that tells the one about the other. After all, the mass of the central supermassive black hole is still small compared with the total mass of the galaxy. It's not affecting the motions of the outer stars. Now, the way we think this works is that there's some sort of co-evolution. That is, as a galaxy assembles, it starts to put together the bits of this central supermassive black hole. And that's going to be a combination of two things. The two key things that are going on, probably, are galaxies colliding with other galaxies and their central supermassive black holes merging with one another. And the other thing is just gas in the neighborhood of a galaxy is not necessarily fully stable when it gets close to the central mass and will tend to drop in. And here's a simulation from a few years ago by Younger et al. Showing the collision of two galaxies and what it does to the mass of the central supermassive black hole. Here's where the two galaxies are in a mass ratio 1:1. Central supermassive black hole essentially doubles in mass and then gains some more because the gas in the galaxies gets so disturbed it wants to funnel into the center. With a mass ratio of 8:1, you get less growth of the black hole, but you still get quite a lot of growth. And it seems to scale with the amount of mass that's in the colliding galaxies, in the sort of way that would keep that 1 part in 1,000 ratio. And if there's just gas around, well, that gas will also feed in. Here's the mass of gas at different radii away from the center of the supermassive black hole, and the mass of the black hole growing at the expense of the nearing gas. And some of the further out gas. And this gas even further out is probably being thrown away rather than going in. And that's this beast being a messy feeder again. And the messy feeding showed up in that picture I showed earlier, because there is this fast outflow, which is going to carry stuff along with it as it goes up or down. These things are sometimes referred to as galactic fountains when the flow is not incredibly fast, but we call them jets when the flow is fast and stays nice and tight over a good long distance. I'd be remiss if I didn't mention quasars in this context. A quasar is simply a galaxy with an active nucleus which is so bright that it outshines the rest of the galaxy. And you have a hard time finding the galaxy because the nucleus is so bright. And quasars get up to around about 2 × 10⁻17 solar luminosities. That is 10 million times the brightness of our galaxy. This is the fraction of the objects that have a particular brightness as a function of that brightness. And because it came from America, they're still using CGS units, for which they ought to apologise. Now, I couldn't resist throwing in one of my own objects. This is Parkes 2152-699 that I've been working on for a while. The picture on the right is a radio map that I made using the Australia Telescope Compact Array. Here's the location of the black hole, the thing I've labelled core, and here's the directed flow that comes out and keeps on going out until it clobbers some external gas in a very strong feature a long way out. On the other side, well, there's another clobbering feature. We don't see the jet so much, and that's because of our friend the Doppler effect. The jet that's pointed towards us looks brighter than the jet that's pointed away from us. And from this we can infer something about the speed of the jet, about 90% the speed of light, and the orientation to the line of sight. Now, I've asserted that jets can cause star formation. In this particular case, that's pretty obvious. Because if I take an optical image of the galaxy and subtract the starlight, you see this thing called the high ionization cloud, which lies at the edge of the jet. The jet has hit it, compressed it, excited the gas, made it make stars, made it get hot, and as one of our students recently showed, has made this gas start to move very quickly away from the galaxy. That is, there's a momentum and an energy transfer to this gas. That's a bit of a ratty old picture. A few years ago, I went off and got a picture from the Hubble Space Telescope to improve matters. Here's the improved picture. I've again subtracted the galaxy. Here's the jet, bouncing off the edge of the ionization cloud and carrying on out. You might well ask, well, what's all this mess? And I've subtracted the starlight in a sort of a smoothed fashion. So what I'm seeing down here is dusty regions and excess brightness regions probably created when this big galaxy ate a small one for lunch. And it's a bit of a messy feeder. And these are the leftovers that are sort of sitting around. And not just sitting around passively, inevitably they will eventually drop in towards the centre. So they're providing future fuel for the central black hole, which could keep this structure running for another 100 million years or so. I'm making it sound as if these jets have it all their own way. In fact, the jet comes out in this direction, bounces off this cloud and is pushed sideways. That is, the clouds do get a punch in to try to make the jets deflect. It's not all a one-sided exchange. And to reinforce what I was saying about the hotspots, up here at the northern hotspot, which is actually the reason why I made this HST observation, we can see optical emission in a nice curvy pattern, which looks like a splatter pattern as a fast flow hits external gas. And that's going to be a location where a lot of energy and momentum is being deposited. The red arrow points to an insignificant looking feature that turns out to be where the brightest X-ray emission comes from. And I think that's to do with a process of the incoming jet seeing radiation from the hotspot and boosting it up. But that is an aside. There's a picture of some of the dust loops again, and again, hundreds more mega years of potential food if it can make its way down towards the centre. Here's another example. This is the galaxy NGC 1265 in the Perseus cluster, another good amateur telescope object. The galaxy is about this big. This is a radio image, and there's this enormous radio trail behind the galaxy as it drops into the Perseus cluster. I think you can also see in this image made by my student, this huge bag of radio-emitting material that has also been ejected from that supermassive black hole. I remind you that the black hole itself is only one solar system in size. The galaxy is only this big. This is a megaparsec. So this dinky little supermassive black hole has contaminated its neighborhood over a region that is more than 10 to the 18 times its own volume. It is really good at providing a smoke screen for itself. Also in the Perseus cluster, a rather more famous example that Andy Fabian has talked about a lot, this is NGC 1275, the galaxy at the center of the Perseus cluster. This again is an X-ray image. The three colours are to do with the temperature of the gas. You can more or less ignore them. You can see these big holes in the gas. Those are bubbles which are being blown by the active galactic nucleus at the centre and are then rising in the cluster potential well, rising in the atmosphere of hot gas as time goes on. Notice they're discrete bubbles. They're not long, thin cylinders or anything like that. That is, the activity that is coming out of this black hole is not continuous, it's episodic. It's being triggered and being untriggered and then being triggered again. So there's a duty cycle behavior going on here. And the reason we only see 5% of all galaxies as being active is presumably that only 5% of the time is one of these supermassive black holes at lunch, getting fed and being able to drive one of these outflows. These outflows, once they happen, fade quite quickly. If you look very carefully, you can sometimes see leftovers, but they do tend to go quite swiftly. I've mentioned this before as one of my favourites, NGC 6251. The galaxy in here is smaller than the tip of my pen. This thing is almost megaparsec and a half across. And look at how the radio emission at the ends has spread out. This has extended not only outside the galaxy, but outside the group of galaxies in which it lives and into the wider intergalactic environment between the assemblages of galaxies. It is contaminating future infalling material that may go into other clusters or groups. It's putting relativistic electrons, we can say that because we can see the radio emission, magnetic field, we can say that because we can see the radio emission, and presumably cosmic rays that we can't see on an enormous scale and doing something dramatic to the wider universe. This you might call sort of feedback behavior. We've seen that the immediate neighborhood of a central supermassive black hole is affected by gravitational effects, but that is limited to a couple of kiloparsecs at the most, depending on the mass of the object and how spread out the stars are. I should say, by the way, that studies of this might be able to find binary supermassive black holes that are just starting to merge, because they whip around like teaspoons in a teacup trying to stir up the stars near them. The intense radiation field these things produce affects material out to 10 kiloparsecs. The outflows go out to a megaparsec. So these tiny little objects are doing a lot. The curious thing is that they're doing a lot in a nicely regulated fashion, in that if you've got an X-ray emitting cluster of galaxies that's trying to cool as it emits the X-rays and drop in, they can be stopped by a supermassive black hole turning on and starting to heat them. But it's regulated in the sense that it doesn't overheat, it doesn't blow everything away, and then you have to wait one universe lifetime for the stuff to start dropping in again. there's a regulation going on here. And the mystery about black hole feedback is, why is the regulation so good? Which is why we keep trying to study the thing. Okay, so let me summarize what I've said over the last 50-odd minutes. Firstly, supermassive black holes are by no means rare. Every galaxy you look at in one of your telescopes probably has a supermassive black hole in it. In fact, the only galaxy I know that doesn't have a supermassive black hole in it is M82, because I've looked for it and it's not there. It's an irregular galaxy, of course, so it doesn't have a nucleus, doesn't have a bulge. And so it's still true that this supermassive black hole to bulge mass ratio holds. Presumably, when it interacts with another galaxy and forms a bulge, bulges tend to form from interactions, it will start to grow a black hole. A supermassive black hole will take in most stuff that's thrown at it in a suitable fashion, either as a lump, say a star, and that will produce a thing called a tidal disruption event, because the local gravitational field at the disruption surface around a black hole of a mass like the M87 one is about 1,000 G. And 1,000 times the Earth's gravitation is certainly enough to cause some disruption to anything. Not only does it accrete, but the local environment can then be a very strong emitter. And a supermassive black hole can easily affect matter on scales 1 billion times its own size, where size here means the size of the event horizon. Simulations have shown that if we didn't have some sort of supermassive black hole feedback, the universe we see today would be very different. Two obvious things would happen. Galaxies would be much bigger. So this has tended to stop galaxies getting too big. And clusters of galaxies would have much less gas, because the supermassive black holes keep the gas hot, so its pressure can keep the gas up and produce the nice X-rays that we see. So supermassive black holes are doing us some good. And let me return to the question I asked at the beginning. Do we need to worry about the beast at the centre of the Milky Way? And my answer is, well, not yet. But if that star S2 gets very much closer to the black hole, it will get tidally disrupted. And when that happens, the centre of the Milky Way will suddenly get a lot brighter. Thank you for your attention.
Thank you very much, Mark. So what about when we merge with the Andromeda Galaxy in something like 10 billion years' time? That's been suggested that might switch on our black hole and turn it into a quasar, which would not be very good for anything on the Earth at that time.
It would definitely start feeding our central black hole and the Andromeda Nebula central black hole. And then those two black holes, because of the tidal drag of the adjacent stars, will tend to spiral in towards one another until they merge. And when they merge, the light show will really happen. And there's this project called LISA, Laser Interferometer Space Array, which is supposed to look for these enormous gravitational wave events that sort of thing would produce. I think you've got to talk after lunch.
We have indeed, yes. So we'll wait for that. Any other questions about black holes? Gentleman in the check shirt.
All galaxies rotate in the same direction?
Well, no. Elliptical galaxies often have very little rotation. And the reason for that is that take a spiral galaxy rotating like this, merging with a spiral galaxy rotating like that, it's flat. Conservation of angular momentum means that the net rotation afterwards is much lower than the original rotation. And if you do that a couple of hundred times, as you need to make an M87, the angular momentum really drops away. Now, once you've got a disk going, and trying to reverse the direction of that disk, you've got real trouble. So, one thing that will happen when the Andromeda Nebula merges with us is that all the angular momentum is going to get stirred up like crazy, and we'll end up in one rather larger elliptical galaxy rather than star. Maybe. It depends on what the residual amount of molecular and ordinary gas is at the time that we need. Because that's what we want to do.
Just one more for Richard Miles.
It's actually related to the size of the supermassive go to its age. You know, how primordial are they? So is M87, and a corollary of that is, do any have globular clusters?
Well, M87 certainly has an enormous number of globular clusters, but you can't see them very close in. And a globular cluster that inadvertently goes into the middle part of M87, whether or not it gets close to the black hole, will get partly disrupted by the other stars. The ages of black holes, well, we can see quasars out to redshifts of 8 to 9. We can see well-formed galaxies out to redshifts of 10. And we believe this supermassive black hole to bulge ratio is still active back there. So some of these black holes will be black holes. But of course, saying how old they are if they can merge with other black holes is which one do you age? So in origin, there will be black holes that are nearly the age of the universe.
The larger the black hole, presumably, the more likely it dates back to an earlier epoch.
Well, bits of it. But how long it's been at that mass is a different matter. So now the masses just gradually ramp up over time, or sometimes quite quickly ramp up over time. The plots I showed over about a giga-year showed that there were jumps of the black hole mass that happened over only about 50 megayears. So you can get quite a lot of change of the black hole mass really quite quickly. Then it hovers for a bit, then it has another good lunch and jumps up again.
Right, well, black holes, very messy eaters. We've got to start our own messy eating now, but don't be too messy, please. So one more round of applause for Mark Birkinshaw. And we will start again at 14:20. See you all then. Can you take your seats again, ladies and gentlemen, please? So we have 3 talks for you now. No, 4. Yeah, we've got 4 talks this afternoon, in fact. In a little while, we will have Dr. Patricia Schmidt, who will be speaking to us over an online connection. But all the other speakers today will be live here in the hall. And first of all, I'll introduce the Secretary of Cardiff Astronomical Society, Greg Titley, who's going to talk to you about the Society and what it does. Right, thank you, Greg.
Good afternoon. I'm going to let you know that I'm joined here with Phil Wallace, our chairman. We're going to do a double act, as per usual. So, first of all, absolute great privilege to be here this afternoon. We're happy to co-host with the BAA and been an absolute privilege to work with you guys, so thank you very much. So, first of all, before we get started, how many of you here are members of Cardiff Astronomical Society? Don't be shy, put your hands up. We've got a few people here. Excellent.
So where were you all on Thursday for my last talk?
Uh-oh.
I'm still slightly miffed about that. I won't bring snacks for the next one.
But that's your mandated role. Anyhow, so a lot of you here are not actually members of the society. So a bit of context. We are the largest society in Wales. We have about a membership of 200, and that means we're one of the largest societies in Britain, which is quite scary, really, isn't it?
It is. They're
Yeah.
the boss in charge.
That's even equally more scary. So, as we hear, some of us may not know who we are. So, why not introduce ourselves? So, who are we? We were established in 1975. Now, I'm happy to reveal, before I was even born, by a few number of years. Okay? I know it looks deceptive. However, quiet you. I know it's you, Teresa. But, anyhow. So we were established after a out-of-London RAS meeting, and it was a discussion, actually, let's have some astronomy in Cardiff, have some astronomy in Wales. Apologies, I'll speak up and put my booming voice on. Anyhow, so, got going, and we have various different arms to our society. We cater for all. I am not an astronomer. I don't even have a degree in physics. I am the black sheep. I did humanities. Please don't judge. But it's geared at all levels, even if you're a complete novice, even if you just looked at the night sky and gone, that's pretty. But what's going on? What is up there? To the point where some of us in our membership are, they've had books published, they have doctorates in their own rights, etc. So we've got a mix of people together. But you don't need a PhD to appreciate astronomy. Far from it. So, as I said, we've got a few parts to our society. Our crown jewel is our observatory. Now, we're really pleased and proud to have this up and going again. So our observatory is located in the National Trust property of Dufferin Gardens, which is a stone's throw away from Cardiff itself. It's out in the Vale of Glamorgan, and even though it's only barely a 15-minute drive from the edge of Cardiff, the dark skies there is not too bad. It's not as pristine as, say, Banabrehanog. Close. I've lived in Wales 23 years and close. But
we're still working on it.
We're still working on it, do forgive me. But there are really good dark skies in the Vale of Glamorgan. And we're really proud of our observatory, which is available to our members. Now, with the observatory, we have a number of standalone telescopes, but we have an 11-inch Calistron telescope, don't we, Phil?
I don't know why you're looking at me for the model number, mate.
Oh, dear, useless.
It's an 11-inch Celestron on a decent mount, I know that.
Fork mount. But this is available for your through your membership, okay? But it's not just sort of, well, here's a key to the building, off you get going. We'll coach you, we'll get you going with it, we'll also show you how to use it, and it's your facility to be used. We also pride of our observatory, which I'll discuss later, with star parties, observing sessions, but it is literally a crown jewel. Now, the other element of our society is star parties. Now, this is where, if you, again, are a beginner, start to become a little bit interested in the night sky, and again, looking up and thinking, oh, that's nice, that's pretty. Come along to a star party where members of the society from all various sort of skill and knowledge level will be able to say, well, that's a Orion Nebula. That's a galaxy. That's the Pleiades cluster. And tell you a bit more, but what are you actually looking at? And this is a really lovely way of introducing you into astronomy. It's how I got into it when I was about that high. With my father who said, well, that's what's going on up there. This is a really nice way to introduce you to the sky, but not just sort of standing there and looking. You've got people who actually do know what they're talking about and saying, this is what you're looking at. We have a range of telescopes from our members and including our observatory. Even if it's a rainy day, we still go ahead. We may use things like stellarium to understand what we're looking at.
Yes, if it is raining or just cloudy, which being in South Wales is more often than not, sadly. Just next to our observatory, there is a National Trust buildings sort of meeting room type thing. Basically plonk ourselves down in there with a projector and a screen and stellarium running on my laptop, and we say, okay, this is what you would be seeing if the skies were clear. Plus useful features like turning off the atmosphere.
That's always helpful, but please don't do that in real life, because Yeah, it's not a good look, is it?
If I had that kind of power, do you think I'd still be a civil servant?
Pass. Anyway,
You mean no comment?
No comment. But anyway, we also do observing sessions. So if you are an established member, you can come along and bring a telescope and learn from each other as well. The best way to learn is not just through a book or watching a YouTube clip and things like that, which is a good sort of way of kicking yourself off and getting from the starting blocks. But sometimes you'll be using a pair of binoculars and a telescope thinking, I'm not quite sure if I'm getting things right, or I wanted to try and achieve something, but I'm not quite sure. Peer-to-peer discussions is, I find, the best way in any form of training to learn from. And this is a really good opportunity to actually work with your peers and go, oh yeah, I had a go with looking at this. Or that didn't work for me. Now, that element is for our practical side. There's people who want to do, say, astrophotography, which Dr. Jane Clark, right at the back, give us a wave. She's also good at astrophotography. And if you're a member, we can get you going with astrophotography as well. Learning how to use the software behind things. How to get your camera to work with a telescope. But that's the practical side of the society. We also have a talks program. So if you're more inclined to learn a theory or to sit back and relax and listen to various parts of astronomy, we have a talks program. Now this runs from September to July, so we have a break in the summer. They're once a fortnight on a Thursday evening. And we pride ourselves in our talks program of getting some of the best speakers we can find. Now these tend to be from professional astronomers who are at the cutting edge of their research. These could be PhD candidates at the start of their research careers. They could be passionate people talking about various elements of astronomy. These are gauged at various different levels. There are some more advanced talks, which, with my A-level physics, is a little stretch at times, but it's a stretch and it's a good learning curve. But some are designed for absolute beginners. Some are quite light-hearted. I mean, our last talk was delivered by our own chair on Project Orion. It was fun. It was fun. It was light-hearted.
And some of you would know if you turned up.
Not that he saw. Much. But it's a really good way of introducing yourself into astronomy. So again, you don't need a PhD to really appreciate it. Now, we get a huge number of different speakers, again, once a fortnight. Now, I'm getting faint again, aren't I? So, I mean, two key recent speakers was Professor Alex Lilly and Dr. Hannah Wakeford. Both delivered fantastic talks. We're also establishing an international talk series. Now, this would be via Zoom. So our talks, fortnightly talks, are done in person. We find, like today's session, you get a better interaction with your speaker. You can have those sort of natural conversations and sort of those natural questions that come up. However, there is a place for Zoom, and we are establishing an international talk series where we'll be getting speakers from the continent, from the eastern seaboard of the United States, and places like South Africa. So individuals from NASA, ESA as well. That will be a Zoom-based one, so you don't even have to leave your own home. You can sit back, relax with a cup of tea. So, at the back of the room, we do have a number of leaflets which have the current year talks program. Have a look. See what interests you. If you are interested in coming along to a talk, there is no obligation to join. Try us for size, as it were. Come along, see how it fits. If you enjoy it, great, sign up. If it's not for you, not a problem. You're more than welcome to come along and give it a try. If you are interested in finding out more, like I said, there's leaflets at the back of the room. I've also put QR codes on the display board so you can find our website and social media pages. Thank you very much.
May just elaborate on a couple of points that Greg raised there. One, whilst the QR codes are an excellent idea, good luck getting a phone signal down here. That does, we may have missed the mark slightly on that one. So please do take a leaflet. Second, the current leaflet with the talks program on it is not accurate. We have had to shuffle things around a bit due to illness and cancellations and so on. So if in doubt, look at the talks program that's on our website, because that will be the most up-to-date one. And third, not that I want to go for a hard sell, but at our last AGM we did have to raise our subscription fees, which we haven't done since 2007, but alas, I move on. That comes into effect from the 1st of August, so if you May, June, July, you can get a little bit cheaper. Just saying.
I mean, yeah, in terms of current membership levels, we pride ourselves of keeping it at a really good price. So currently, for an adult membership for a year, which includes access to the observatory, our library, which is quite extensive, the talks programme, is £15 per year per adult. Come the 1st of August, that will raise to £18 per year. A family membership is 20, and that's going up to 25? 24 even. So it's cheaper than a magazine subscription. So, but if you're interested, come along, have a chat afterwards and see if you want to become a member. Any questions? Give us a shout.
And as you can see there, we are, I was going to say we're active on social media, it's really just Facebook at the moment. We're working on improving that, but neither of us have any interest in Twitter or Instagram.
What's Twitter?
I don't know. Someone tried to explain it to me, and it's just straight off my head. Yes, we have the library as well, as Greg mentioned, with a number of books, both current and some quite historical ones, which are available to borrow for members for free and for pretty much as long as you want, as long as we get them back. Because if they don't, he's a tax man and I work with bailiffs, we will hunt you down.
That's a promise.
Yes. Yeah, and as you said, there's no obligation to join. First one's free. Just come along, introduce yourselves, and if it is a good fit for you, then by all means, stick around. Because if you turn up for the second one, we will be coming after your wallet. It's important to establish these things honestly.
Absolutely. Any questions? No. Thank you very much for your time.
Well, thanks very much, Greg and Phil, and thanks very much for all the help of Cardiff Astronomical Society in organising this meeting. These meetings around the country the BAA organises. We're very dependent on having good and active societies like yours with good organisers to establish the local contacts and tell us where the good venues are, and round people up, of course, round all the local astronomers and astronomically interested lay people to give a good audience to our speakers. So our next speaker is going to be on Zoom. So let's see if we can establish contact with Dr. Patricia Schmidt.
Yeah, I'm the director of the historical section, and the next BAA meeting is this time next week, next Saturday, May the 20th, at the Birmingham and Midland Institute in Birmingham. And I'd like to tell you a little bit about it as we have a minute or two before our next speaker arrives. BMI is a very centrally located in Birmingham, in the city centre, within 10 minutes or so walk of the train station. As far as I know, next Saturday there are no train strikes, fingers crossed, or Eurovision Song Contests, or coronations, or cup finals, or anything else. So there's no excuse not to come along. You can also get there by car. I probably will. If you are, it's in the middle of the Birmingham Clean Air Zone, so check whether or not your car actually it falls foul of the regulations. We have, I think it's a pretty good speaker lineup. We have Mark Edwards, who will be starting things off by talking to us about the early history of the Jodrell Bank Observatory. Mark actually did his PhD there, not quite in the early years, but in the 1970s. But he knows a lot about the history of that venerable institution. And then we have Marie-Louise Archer, who's on the BAA Council. Marie-Louise is a very, very well-travelled lady, and she visited Ulugh Beg's observatory in Samarkand, which was probably the world's leading observatory about 600 or 700 years ago. So she'll be telling us about that observatory and about the man who founded it, Ulugh Beg. We were then going to have a speaker about the Egyptian astronomy, ancient Egyptian astronomy, Dr. Pauline Norris. Unfortunately, she's had to drop out. So at quite short notice, our archivist, John Tutor, is going to be telling us about some of the recent additions to the BAA archives, including, I'm told, some footage from the famous Monte Umbo expedition to see the solar eclipse of 1973, which is quite famous in BAA history. Patrick Moore writes a lot about it in his books. And then we have Lee MacDonald, who used to be my deputy as the director of the BA historical section. He's currently he's a professional historian, and he's currently researching the history of the Greenwich Observatory. So he'll be telling us about the Greenwich Observatory during the Great War, when many of the staff went off to fight, and those who remained continued to do astronomy, and of course the women who were involved as computers in the Greenwich Observatory finally came to the fore as part of the observing staff. And finally, somebody I've been trying to get for the BAA historical section for many years, Andrew Lound. I don't know how many of you have seen him. He's a superb presenter, very theatrical style. He usually does his talks in costume. He will be telling us about Herschel's lunatic astronomers, the connections between William Herschel, the great observer, the guy who discovered Uranus and catalogued so many nebulae, and his connections to the Lunar Society, who met in Soho House, Handsworth in Birmingham, on the night of the full moon, so they could walk home safely. And that society includes Matthew Bolton, James Watt, who used to be on the £50 note, Joseph Priestley, Erasmus Darwin, Josiah Wedgwood, and so many people from the early history of Birmingham. And they were connected. They corresponded with William Herschel and the Herschel family in Bath. So I think it's a pretty good programme. It covers almost all aspects of the history of astronomy, and I hope very much that you might consider coming and joining us. There are still places left, so look on the BAA website and you'll be able to join there. So thank you very much for giving me some time. Thank you.
There's a question at the back there.
Did you pay for individual talk, or is it for members?
It's for members, you pay for the whole day.
Okay. Yeah. So each talk you pay for the whole day, you have set up. Some of it sounded quite really interesting.
It's a full day conference like today.
It's open to non-members.
And you've got the information
is on the website, on pretantro.org. It's £7.50 for BAA members, £10 for non-BAA.
Oh, that's good.
£10 for non-members, £7.50 for BAA members. Hello, Dr. Schmidt.
Hello, good afternoon.
Right, we can see you and we can hear you. That's lovely. And where are you today?
In Birmingham, due to the train strikes, unfortunately.
You're in Birmingham, right. Dr. Schmidt is originally not from Birmingham. She's originally from the equally lovely city of Vienna in Austria. She did her PhD in physics and astronomy here at Cardiff University in 2014. After that, she went to work on gravitational waves as a researcher at the famous LIGO Observatory in the USA, and also she worked at Radboud University Nijmegen in the Netherlands. In 2019, she went to the University of Birmingham, where she became an associate professor. Her research focuses on theoretical modelling of gravitational wave signals emitted by colliding black holes and neutron stars, which is exactly what she's going to elaborate on now. So please give a warm welcome to Dr. Patricia Schmidt, who is going to talk about gravitational waves, messengers from the stellar graveyard.
Thank you very much for this really lovely introduction, and my sincere apologies that I cannot be with you in person today. I would much rather be down in Cardiff than here in Birmingham, and I'm sorry you have to suffer through another online talk, but hopefully they'll be exciting and we'll have a fun time together exploring this relatively young field of astronomy that is gravitational wave astronomy. And in the spirit of today's theme of the meeting, we'll be talking about specifically the messengers from the stellar graveyard, so from the remnants of very massive stars that you have explored hopefully already in previous talks. Now, to meaningfully talk about gravitational waves, we have to go back to the beginning, and that means we have to talk a little bit about general relativity. It all changed at the beginning of the 20th century when in 1915, Albert Einstein, famed German scientist, revolutionized really our understanding of one of the four fundamental forces. And of course, gravity has been around for a very, very long time. Newton's theory, very, very successful, but then they came along the sky and turned everything upside down with something that looks like a rather complicated version of the sort of phenomena that we are very, very familiar with. But I'll talk you through some of the very basics in order to understand where gravitational waves come from, because it's really important. Newton's theory of gravity does not predict gravitational waves. So we really can't, view this in the sense of Newtonian gravity, and we just have to take the leap and look a little bit at Einstein's mathematical theory of relativity. So in a nutshell, kind of to set the scene, some of the key differences between our classic picture of gravity that we have from Newton, where time and space are absolute. They are not really entwined quantities, and they don't change relative to each other. And gravity is an attractive force that is exerted by any masses that we have. And of course, there's the famous picture of the apple falling down. Our standard everyday experiences, I think, are very much in tune with classical Newtonian gravity. But we can't explain all observations with it. And so it was very early on recognized that we need some form of extension of Newtonian gravity. Of course, in certain limits of the theory, Newton's picture is perfectly fine. But there are things that Newton can't explain, and that's why we need to go beyond. And what Einstein did in 1915 with some, especially mathematicians, working in the lead up to this, was to develop a more mathematical picture of this fundamental force by combining effectively time and space. So they're no longer these two separate absolute quantities, but they now form a four-dimensional space-time continuum, and they have relative effects onto each other. And in this kind of picture of this four-dimensional space-time, gravity itself is not viewed as a force like we do Newtonian gravity, but it manifests itself as a very specific mathematical property. And that property is called curvature. And we then write down, rather than Newton's relative simple inverse square law of gravity, a more complicated equation. And that essentially encapsulates the main feature of this general theory of relativity, which tells us that matter curves the space-time, so any form of matter that is present, illustrated here by some exaggerated sun. And on the other hand side, this curved space-time, if you have an object in it, it tells it how to move. So we have this interaction between the curvature of space-time and the motion of, for example, the celestial objects. This sounds maybe a bit like, science fiction. Is it relevant for us in our everyday life? Yes, absolutely. And I think all of us like to use the sat-nav when they go to a new city or they have to drive somewhere where they haven't been before. And that is one of the very nice everyday applications, I would say, of general relativity. And it's really, really important that we don't just trust Newton here, but that we actually have the full theory. What we use when we use our sat-nav is, of course, a GPS. So we have satellites positioned about 20,000 kilometers above the Earth, and they have clocks that communicate with each other. And the timing of these clocks is very, very crucial. And it is affected by the fact that our Earth has a gravitational field. It's a massive body, so it curves the space-time around it. And that leads to the famed effect of time dilation. So clocks work differently, or they tick differently when you are in a gravitational field, and that effect gets stronger and stronger the stronger the gravitational field is that they are in. So if you have these clocks now sending information to find the position on your sat-nav where you want to go to, if you didn't take relativity into account, and after one day those clocks would be out by 17 milliseconds. Well, that sounds like nothing, 17 milliseconds. What's that? But it translates into a position error in your GPS and the sat-nav of 5 kilometers. So since you folks are in Cardiff today, obviously, if you're an avid rugby supporter, you would very much like to end up, hopefully, in the Principality Stadium and not get misdirected 5 kilometers elsewhere. So it really has an everyday impact. And I like to say this to people because often it seems like, a very, very complicated mathematical construct, but it's very, very relevant for our everyday applications. Beyond, of course, the application of the GPS, it makes very concrete predictions. And that's always fundamental to any theory that we look at. We want a theory that makes concrete predictions that we can go and test and then either confirm the theory or falsify it if the observation does not fit with the prediction that are being made. And the very famous ones, so there's a series of them very early on after the theory came out in the early 20th century, was, of course, the deflection of light. This is kind of illustrated in this graph on the left-hand side here, where we can see the sun making this dent in the space-time because of its gravitational field. And here we have the Earth, where we have astronomers observing various aspects, and a position star in the background here. Now, the light that comes from the star that we would like to observe on Earth, for example, with our telescopes, is affected, like everything else, it's energy that is affected by the curvature of space-time induced by the sun. And so what happens is the path that this light, this photon travels, is being deflected in the gravitational field. And that makes a concrete prediction for how large this deflection should be. And we can go and measure this. And well, we didn't, but Eddington did with colleagues way back in 1919, the very famed eclipse, where I traveled to South America, and did indeed find a measurement that was consistent with the prediction made by general relativity. And you can see here an example of the papers that were very, very excited. And apparently nobody need worry after this was successfully measured very, very early on. There are other effects that general relativity predicts, like the perihelion precession of Mercury. You know already from Newton that objects in a two-body system out there, like all the planets, follow elliptic orbits. But what we do find is that the orbit that Mercury traces out doesn't quite fit with the predictions from Newton's theory of gravity. And that is due to what is called this perihelion precession. So you can see the ellipse that is being traced out here around the sun, here at the perihelion. And what you can see is that the orbit, as Mercury goes around, it precesses. The relative orientation in the plane of the plane itself changes by a certain angle per century, and Newton predicts that should be 38 arc seconds, and general relativity tells us it should be a bit larger, and the measurement indeed agrees significantly better with the prediction in general relativity compared to Newton's gravity. So there is a lot of evidence in favor of general relativity in certain regimes where it becomes relevant. Now, there are some more exotic predictions by this theory as well. And one of the, in my opinion, most exciting prediction is the existence of what is called a black hole. In a nutshell, a black hole is an area of space-time that is so strongly curved that not even light can escape, hence the name black hole. It was first described essentially a year after general relativity was published in 1916 by German astronomer Carl Schwarzschild. And they are actually, mathematically speaking, very simple objects. They're described by their mass. They're described by their rotation or their spin, if they have one. They don't necessarily need to rotate. And they could, in principle, also carry some electric charge, though for astrophysical black holes, so the ones we're interested in when we look at into the galaxy and beyond, they normally do not. We don't expect them to have an electric charge. So, you know, they're actually very, very simple. You've heard about stars before. Stars are way more complicated to describe than black holes. And one of the properties that you can use that you often read about is the Schwarzschild radius, which is essentially the size of the event horizon, which defines this area beyond which no light can escape anymore. Now, this sounds maybe quite exotic, but it's actually not from an astrophysics perspective, because massive stars, so all stars essentially that are heavier than about 8 to 10 times the sun of the mass of our own sun, eventually collapse into what is known as a compact object. And one form of a compact object is a black hole. So we do expect them to actually form very, very regularly out there at the end of the life cycle of massive stars. And that's shown here in this circle of life diagram, where we have a massive star that burns and fuses elements as it goes along. But as it starts to run out of fusion material in the core, it can no longer support the gravity. And so it starts to collapse on the interior. And depending on how heavy it was initially, it either forms a black hole, which are these funny mathematical predictions by general relativity, or a neutron star, which is a very, very dense star, very small, very dense star on the order of 10 kilometers in radius, formed of nuclear matter. So neutrons, very, very densely packed neutrons. So black holes, astrophysical black holes from stars, we expect them, to be out there in quite a large number. And of course, we don't only have to look at the small black holes. We can also look at the very big black holes, like the ones in the center of our galaxy or our neighboring friends. And this is, in fact, what we have been doing when we talk about observing black holes, because they are black, we've just said no light escapes them. We can't just look directly at the black hole using electromagnetic observations, but we can indirectly observe them through electromagnetic observations, and there are some very famous ones. So here you can see systems where we have a star and a black hole, and the black hole is feeding on the star, so it's extracting matter from it, forming an accretion disk, and maybe, depending on the properties, also forming a jet-like structure around the black hole. So we can look at the dynamics, we can look at the electromagnetic emission that comes either from the jet or from these accretion disks that are being formed, and then can indirectly infer something about the properties of this feeding monster in the center here, and that can be in a star system, but that can also be the case in galaxy centers and stars very nearby. You can see here an example for a tidal disruption event where you have a black hole and a star coming by and being a little bit too close. And if it's too close, it becomes tidally disrupted due to the gravitational forces of the black hole. And that also forms an accretion disk, but most importantly, it forms a very specific and a very characteristic electromagnetic signal that, again, classic astronomers, so to say, can observe with their telescopes. Very famous, of course, in the last couple of years, big in the news, the images, the first images of black holes at the center, supermassive black holes at the centers of our galaxy, Sag, but also M87. And here you can see the picture for M87. And again, what is being looked at here is actually the radiation that is coming from outside the event horizon, where you have matter surrounding the black hole. And then something that also won, of course, the Nobel Prize not too long ago, were indirect observations, again, of our own center of the galaxy, so not just with the EHD imaging, but observing the motions of stars. And that is shown in this little animation here by Andrea Gertz's group at UCLA. And in particular, if you look at the yellow line here, you can see a very special star. This is star S2, which was observed for almost 20 years and tracing out a complete orbit. And we can use the observed dynamics of the star to trace back how large the black hole, that central mass, has to be in order to explain the dynamics that is being observed by the stars. So these are kind of examples of what I would call indirect observations, because we're looking actually at the impact of material, of stars, of baryonic matter around the black hole and how it is impacted, and then make inferences about what the mass distribution in the center has to be, and find it is consistent with a black hole of a certain mass or a certain rotation period. But is there a way of directly observing black holes? And the answer is yes, because even though they don't emit light, they, if under specific circumstances, are capable of emitting gravitational radiation or gravitational waves. And in a nutshell, gravitational waves, they are just periodic vibrations of the fabric of space-time itself. So think about a wave like you would think of an electromagnetic wave, but now it's not created through some processes, but it's created by actually shaking space-time itself. And these perturbations that you induce, this is what a gravitational wave is. And they travel just as electromagnetic radiation in general relativity at the speed of light. And they are generated very similar to electromagnetic radiation. You may recall electromagnetic radiation is generated by accelerating charges. Now with gravitational waves, they are generated by having accelerated masses. And that can be any anything, you know, us jumping up and down will generate gravitational waves, very, very tiny ones, but will still generate gravitational waves. But the prominent candidates in the universe for generating gravitational waves are some of the most exciting and cataclysmic astrophysical events. And one that I'm particularly interested in are these collisions of two black holes, because that's a way of actually looking directly at the black holes themselves through the gravitational waves that they generate. And how this works is illustrated in this little video here, where you can see a mass in the center here, and you have a smaller mass going around here, or a smaller object. And what you can hopefully see is that space-time itself, due to this accelerated motion, so motion along a circle is an accelerated motion, becomes perturbed. And what you see is you see these vibrations, these waves, traveling outwards from the area where they are being generated. Now, what happens in a binary system like this one here in particular is that the wave extracts energy from the orbit, and eventually what this will mean will that these two will collide and will clash into each other and give off a very, very large burst of gravitational radiation. But that's not the only source. As I said, any form of accelerated mass can generate gravitational waves. But in order for us to be able to detect them, we are kind of limited by looking at various frequencies or wavelength of the gravitational wave that is being generated, similar to when you look at standard astronomical instruments and you have different types of instruments for different parts of the electromagnetic spectrum. And it's a similar story with gravitational waves. So what this kind of spectrum plot is meant to illustrate here, an analogy to the electromagnetic spectrum, is the gravitational wave frequency here at the bottom, and at the top you can also see the period, so how long it will take for one cycle of the gravitational wave. And overlaid you can see different types of astronomical objects and astrophysical processes that generate gravitational waves in the different frequency bands. Now, if we look at the entire spectrum before we zoom in, then what we see here is a line that spans essentially all the frequencies, all the periods. And this is what we would associate with early universe processes. Of course, there was also a lot of mass accelerated. Stars didn't exist then, but there were other processes that would create accelerating masses and hence gravitational waves. But depending on the process itself, there will be a very different wavelength. And they would form kind of a sort of a stochastic noise background that is the superposition of all these gravitational waves from these processes in the early universe. And they will be across all the ranges. If we look at colliding galaxies with supermassive black holes, so millions to billions times the mass of our sun at their center, and they find each other and start to merge with each other, then we expect them to be emitting gravitational waves on the order of 10 to the minus 9 hertz, roughly speaking. But then as we go to higher and higher frequencies, so that's why the previous slide said the sound of space-time. So when we're looking at a few hertz up to kilohertz, which is our audio band, if we compare it to the human ear, then here we're talking about objects that are a few times, maybe up to a few hundred times the mass of our sun, and form these compact systems like stellar mass black hole binaries, but also these neutron star binaries. But we can also look at the life, at the end of the life of massive stars themselves when they go supernova. That obviously is an ejection of mass, lots of mass being accelerated out here. That creates gravitational waves on the order of a few kilohertz. And even isolated neutron stars, because most of them are not perfectly spherical, but they kind of wobble a little bit around, and that induces also gravitational waves. And they all are emitted in this regime here of a few tens to a few kilohertz. And this is where our current generation of gravitational wave observatories is operating. So we're specifically looking for objects that emit gravitational waves in that frequency regime. Now, gravitational waves were actually indirectly detected already quite some time ago in the 1970s through the observation of the famous Hulse-Taylor pulsar. So a pulsar is a binary neutron star system. So we have two neutron stars, not black holes here. And we can observe them in the electromagnetic because they are two stars. We can monitor in particular their radio pulses. So that's where the pulsar name comes from. It has a strong magnetic field and has radiation along the magnetic axis that sweeps through like a lighthouse effect. And through this, we can measure very accurately the period of the pulsar as it goes around its companion star. And general relativity tells us if they're close enough together, they should emit quite a decent amount of gravitational radiation. And that means the orbit will decay and eventually they should collide with each other. So over many decades, people have observed this pulsar system, and you can see the measurements in the dots in the plot on the right-hand side here, and have compared it to the prediction of general relativity for this decaying orbit due to the emission of gravitational waves. And that's the line you can see going through here. And we see exquisite agreement. So the indirect detection of gravitational waves has been around for quite a while, but it isn't a direct measurement of the wave. It's not measuring the wave and, learning from the wave about the properties of the source that has generated that wave. That only happened in 2015. Now, how can we measure gravitational waves? How can we actually detect them directly? Through the effect that they have on matter. So we have seen gravitational waves travel outwards from the generating source. They travel at the speed of light. But what happens when such a wave now is traveling through space-time? So this is kind of illustrated in a sketch here. So this is my poor man's version of a 2D breakdown of space-time, where you see the grid, which are my rulers, so I'm measuring distances. Now a gravitational wave comes through, it travels into our screen here, and what you see is my grid suddenly gets very distorted. In one direction, it gets stretched, and in the direction orthogonal to it, it gets squeezed. This is what the gravitational wave does. You have an unperturbed area of space-time, and then you have this perturbation traveling through. And what this perturbation does, it induces this characteristic stretching and squeezing of space-time. And it's this little effect that we want to measure when we talk about detecting the gravitational wave. So how large is this effect? It's really, really small. For comparison here, you can see a human hair, which has a thickness of about 0.1 millimeters. In comparison to that, we look at an atom, which is a millionth time smaller than the diameter of a human hair. And then if we look at a proton, so the nucleus of a hydrogen atom, this is on 10 to the minus 15 meters. So that's another 100,000 times smaller than that. And so the average length change, so this average stretching and squeezing that a gravitational wave, even from something like two colliding black holes out there in the universe induces, is another 1,000 times smaller than the size of a proton. So this is really, really small. So when I said, if we jump up and down, we generate gravitational waves, yes, we do, but there's no hope that we could measure them. We really need some extraordinary events out there in the cosmos in order to measure these really, really tiny length changes that are being induced by gravitational waves. And that requires us to have precision instruments. And the way we do this is we use interferometry. The concept in principle is identical to what Michelson used way back at the end of the 19th century when he tried to prove or disprove the existence of the ether. So we have a laser system, we have a mirror, we have a beam splitter, and we have two arms that are orthogonal to each other. And we send the laser light down these arms and have them recombine and then measure if one of those arms was affected by a gravitational wave, then its length will slightly have changed, and that will have induced a specific phase shift that we can measure in our gravitational wave detector. And I run this video where you can see much better what I have just tried to describe in words. So we have the laser going through the beam splitter, going to the end stations. Now imagine a gravitational wave's coming through, very exaggeratedly shaking our gravitational wave detector. And let's zoom in here. So we have our laser light traveling in one direction and in the direction orthogonal to it. It gets reflected at these mirrors at the end. The light recombines at the beam splitter and then gets measured at an output photodiode. Now what we see here is obviously perfect interference here. And then depending on the length here, the length change that was being induced, we can see a characteristic pattern of dark and light fringes on the output here. So if you have a gravitational wave coming through, then one arm gets slightly stretched and the other one gets slightly squeezed, and that will modify the phase coherence between the two laser beams after recombination. That is the principle, how it works. In reality, it looks way more complicated in the detectors. So they are really high precision, very, very fascinating instruments. With, just to give you a flavor here, it's not just two kind of mirrors and a beam splitter. There is a lot more technology here. And in particular, as we want to measure these really, really tiny changes of, 10 to the minus 18 meters and smaller, we have really high precision instruments here with fantastic technology. We need to be very careful about isolation of noise sources. Anything that can shake the detector could mimic a gravitational wave. So we really need to be careful about that. For example, if we're having incredibly high seismic isolation on the mirror side. So here you can see the mirrors, which are about 40 kilograms in LIGO. They are suspended from a multi-stage pendulum in order to isolate it from motions of the Earth itself and other seismic perturbations. We operate in vacuum to avoid any other things hitting our mirror, of course, other than the laser light. So it really is a fantastic machine and one of the most precise rulers that have ever been built. And they're really important in order for us to actually measure these gravitational waves. And here you can see a look inside with a few pictures from the actual site. You can see here the mirror, highly, highly polished mirror. One of the most pure surfaces you can imagine. About only 1 in 3 million photons gets absorbed on this mirror. You can see the vacuum chambers here along the laser lights and parts of the suspension system over there. Currently, our observatories span the globe. There are 2 detectors, the LIGO detectors in the United States. There's the Virgo detector in Pisa in Italy. There's a smaller scale detector that is mainly used for R&D, but also for looking specifically for supernovae explosions in Germany. That's GEO 600. And the most recent partner that's joined us is Kagra in Japan, building the Kamioka mine, where you also have the Juno experiment Super Kamiokande. And in the near future, we also hope to grow with partners hopefully joining in India, maybe in China, maybe also in Australia. So we'll see what the future holds for the global international gravitational wave detector network, all operating with the same principles on the laser interferometry. Now that we have these fantastic machines that can measure such small length changes, it was in 2015 when the first gravitational wave signal was detected. It happened on the 14th of September when LIGO switched on after some technological upgrades and for the very first time directly listened to the collision of 2 black holes. And I hope you can hear the sound. You should hear what this sounds like to the human ear. In slightly 2 different filters, so hopefully you could pick it up, I hope, in the audience. And what you can see here is the visualization of the gravitational wave data in a specific representation. So what you see here is time on the x-axis and frequency on the y-axis, and you can see the results from the LIGO Livingston detector and the LIGO Hanford detector. Those were the only 2 detectors that were operating at the time. And what you've heard is the sound of 2 colliding black holes, what we also call a chirp signal, because you could see how this frequency was just sweeping up and then it stopped. And that is exactly what happens. As the 2 black holes go around each other, the gravitational wave frequency increases until it reaches a maximum, which is the point at which the 2 black holes collide. And then what's left over in general relativity is a black hole that is initially still a little bit perturbed after this very traumatic collision with its partner. But eventually these perturbations get radiated away and it settles down into a quiescent state, into either a Kerr black hole or a Schwarzschild black hole, and then is no longer visible to us. So it's gone truly black again. It no longer is emitting gravitational waves. And we can see this very nicely here in both detectors. Very loud, very, very clear signal. And so I've been telling you, oh, this is clearly a collision of two black holes. So why should you believe me that this is a collision of two black holes? Or why do we know that this was the collision of two black holes? Well, it's gravitational waves. I like to call them cosmic fingerprints. They have a very, very clear prediction and a very clear shape. And they encapsulate very clearly the three different stages that this black hole binary undergoes in the process while it's emitting gravitational waves. So while they are quite far apart from each other, many tens of kilometers, they're already going around each other in orbits and emitting gravitational waves. So the orbit successively gets smaller and smaller and smaller. And what this means is that the speed at which they're traveling gets larger and larger. Then they collide, and then eventually that single black hole that is being formed just rings down, as we call it, like a bell. When you strike a bell, it rings down, and then it goes quiet. And that is exactly what the prediction looks like. So here you can see actually a simulation in full numerical relativity, solving the Einstein equations fully. And this is what you get. You get this beautiful chirp signal that if you transform it into the frequency domain and plot it versus time, this is exactly what you see. And this is exactly what we saw in our data. And it's unique for every binary that you look at. It really is like a fingerprint, or the DNA, so to say, of each binary. And we can characterize our sources, so these observations that we have, by taking these theoretical predictions and comparing them to the millions against the data. And that's exactly what we do. And then we can tell this was a black hole, it was that heavy, it rotated, etc. And here you can see the agreement between the data of the gravitational waves from the first detection versus the predictions from full general relativity. And they show really exquisite agreement with each other. So we are very, very certain that this indeed was the collision of two black holes. And this was only the beginning, but it was a very, very exciting beginning, because what we saw were two black holes that were 36 and 29 times the mass of our sun. So pretty heavy objects there, which we hadn't observed before. We had observed lower mass black holes indirectly, and we had observed the very, very massive, supermassive black holes indirectly before. But now we have objects that are kind of sitting there in between and are a few 10 times the mass of our sun. It was emitted, actually, it travels at the speed of light, so the collision itself happened actually a long time ago, roughly when the universe was about 12.5 billion years old, and today we are at 13.9 billion years roughly. So it's been around there for quite a while until it reached us, and it was very, very small in terms of the perturbation that it actually induced, really giving credit to the fantastic machines that have been built in order to detect it. And it was only the beginning. Since then, LIGO has been operating. We turned off for further upgrades in March 2020. And what you can see here is our stellar graveyard, because what we're looking at are the end products of these massive stars at the end of their lives when they find a companion and create these gravitational waves. And we have observed on the order of almost 100 to date. In blue, in particular, you can see the black holes, and you can see the small dots, which are the two black holes as they were clashing together, and then the big dot at the end is the remnant mass that the object had that is being formed. So to give you a feeling for the very first detection, roughly about 3 solar masses were radiated in gravitational energy. So quite a lot that was converted here into gravitational radiation, even though we can't see it as an energetic outburst like we do with electromagnetic radiation. These are some of the most energetic phenomena that have been observed in the universe. But we didn't only observe black holes, we also observed other creatures, and that we'll talk a little bit about in a minute. But first, let me pick out 2 of these black hole binaries in this big manta ray-like graveyard plot that are particularly interesting, I think. So the first one was GW 190521, discovered on the 21st of May in 2019. That's the postcode here. And it was particularly exciting because it was the first confirmed intermediate mass black hole. So when we talk about an intermediate mass black hole, we talk about black holes that cannot have really formed from direct stellar collapse due to nuclear processes. And so they're larger than about 50, 60 solar masses. And they formed something that was about 142 solar masses heavy in the end. And there have been electromagnetic observations before, which were hinting and hoping for the discovery, but many of them went away. But the gravitational wave is very exciting because there was, under the assumption of general relativity being the right prescription of the system, this was a very clear detection of an intermediate mass black hole. But there were other things like 1908-14, where we had one object that was a 20 solar mass black hole. But what the nature of the secondary is remains unknown to this date. We have measured the mass of this object, and it lies at around 2.6 times the mass of our sun. And that is particularly interesting because it means that it is heavier than any known neutron stars, but lighter than definitely known black holes. So, it could be either, in principle, it could be something completely different as well. It could be some form of exotic matter, for example, if this is an idea you'd like to entertain. But it's meant to show you that there's a lot we can learn, but there's many things that are still unknown and that active research in our very exciting but still very young field. So lots of opportunities there as well. And there are many more. You have seen there are 100 observations. I'm sure if you take a look, you'll probably find your personal favorite binary black hole out there. But it didn't end just with the black holes. In 2017, in August 2017, we observed another kind of gravitational wave. And this time, it came very clearly from the collision of two neutron stars. So these very compact, very dense stars that form when not so massive stars reach the end of their life. And you can see, again, these time frequency plots that I've shown you before, but now for this binary neutron star signal. And you can already see it looks quite different. It's significantly longer. It also looks a bit fainter, even though it was actually a bit louder in our gravitational wave detectors. But most important, you can see it as a very, very long duration signal. Here you can see many, many seconds, whereas this black hole collision that I've shown you before was less than a second long in the sensitivity region that LIGO could detect. And that is a key signal here that we have actually neutron stars, or at least two objects that are very, very low in mass. The lower in mass, the more time they spend at the low frequency part of our gravitational wave detectors. And that's why we can see them for such a long duration. But they were not only observed, not only gravitational waves. This was really a most spectacular observation. And I think the aftermath is one of the most observed astronomical objects, if I'm not mistaken, because it was observed not only in gravitational waves, but throughout the entire electromagnetic spectrum. And here's a nice animation that shows you at least the connections to the high energetic gamma ray observation that was also made in conjunction with the gravitational waves. So you can hear the gravitational wave. And then about 2 seconds later, NASA's Fermi satellite registered very high energy photons, gamma rays, from the same location. So we had a coincident observation of a gravitational wave, which to us it comes from something that is less than 2 solar masses heavy per object, in conjunction with this high energy gamma ray burst. And this was absolutely spectacular because it had been hypothesized for many decades that gamma ray bursts, which are some of the most energetic electromagnetic events in the universe, are created by the collisions of neutron stars or neutron stars with black holes. And now there was definitive evidence that indeed they go hand in hand. So at least some types of these gamma ray bursts can be identified with the collisions of two neutron stars. But it doesn't end there, because for the neutron stars, they're made of matter. So you get a wonderful observation across the entire electromagnetic spectrum, especially once you continue waiting and you look at the various nuclear processes that are going on. So what it was also observed with in conjunction is what is known as a kilonova. And there's an artist's impression shown on the right-hand side here. Because we have all this baryonic matter that gets flung out in the collision and then interacts with the interstellar medium, what we also have is we have chain reactions of nuclear processes, and they create, of course, electromagnetic radiation across the entire spectrum. And that was also, again, an hypothesis that was put out that we expect this type of electromagnetic transient in the collisions of two neutron stars, and now everything all together was being observed. And I think it was a very, very exciting and well-celebrated moment in transient astronomy and gravitational wave astronomy. And it gives you a flavor of how much more we can learn about things when we look at them from different angles and with different methods. And in particular, what we learned is that these neutron star collisions are the birth site or the production site of heavy elements. So many of us wear jewelry. A lot of this is made actually in the collisions of the emerging neutron stars. And that was also a very, very exciting insight and discovery to understand. But neutron stars themselves are interesting for many, many reasons. In particular, because they are such extremes objects. They're unique astrophysical laboratories, and it's very difficult to create the conditions that we expect to be present in the core of neutron stars in lab-based experiments. And that's why having astronomical tools, be in the electromagnetic or complementary in the gravitational waves, to look at them, we can actually learn about fundamental physics. And that is something that is very, very exciting. And to give you a flavor, if you take a teaspoon of neutron star matter, this is how heavy it would be. So these are really extreme objects out there in the universe. And it's very hard, even at the LHC, to create such conditions. But with gravitational waves, we can actually learn about what the conditions of matter are on the inside. And that is because their gravitational wave signal, relative to that of a black hole, looks a bit different. So it comes back to me saying it's the DNA or the fingerprint. There's a tiny, tiny difference in the gravitational wave signal between two black holes, which are just, strong curvature vacuum, versus when you have objects that are actually made of matter. And we can extract that and really learn about the conditions of the matter deep inside the neutron star, something we cannot probe with our ground-based collision experiments, for example. So these observations to date have told us many exciting things about the universe. Well, first of all, gravitational waves indeed do exist, which is very nice to confirm, but also black holes exist, and they come in many different shapes and forms and sizes. Some are rotating, some are not. Some are very light with just a few times the mass of the sun. Others can be, 100, 150 times the mass of our sun. We can all see them in gravitational waves when they find a companion partner and generate them. They look and they behave as predicted by general relativity. So we have confirmation, again, of another kind of energy scale of general relativity predictions that it's indeed doing its job as anticipated. And they occur from some of the most energetic phenomena out there in the universe, like also the collisions of neutron stars, which we have now identified as being precursors for gamma ray bursts, production sites for heavy elements. And from the gravitational wave, we have also learned that neutron star matter is what we call rather soft, which means neutron stars are very, very compact, very small, and they're actually quite similar in their behavior to black holes, but not quite. So lots of exciting things that we have learned to date. And a little advertisement, we're going to start observing in 11 days again. So LIGO has been down for more than 3 years now, and they go in upgrades. But we are very excited to turn back on the 24th of May. So do watch out for some hopefully exciting news. Obviously, we will continue to observe black holes and neutron stars. But as I've mentioned before, there are other classes of gravitational wave sources. So maybe we'll be able to observe some of those with the improved detectors. And of course, there's always the excitement of having some surprises and some things that we haven't thought about and that we need to think about more carefully. And if you look at the long-term future, then we're looking at different types of detectors and exploring the universe even deeper than we are able with the current generation of gravitational wave detectors, and also exploring other sources. So for the ground-based generation, we're looking at larger detectors, which will allow us to observe binary neutron stars, neutron star black holes, and binary black hole collisions effectively out through the entire universe, where we believe that these objects have been created. They weren't created in the very early universe. It took some time to actually form these stars, the first generation being the population 3 stars that we'll be able to access. But if we, want to go bigger in terms of mass, so looking at the supermassive black holes, for example, in gravitational waves, then we have to lift into space. And that is planned for the LISA mission, also both of these to be run, hopefully, by the mid-2030s, the late 2030s. And that will open our horizon and allow us to observe, other sources and observe the sources that LIGO sees when they were very far apart and moving at much, much slower speed. So we'll have even more exquisite tests of general relativity and its predictions. And maybe also be able to say more things, for example, about what is called the equation of state, but of white dwarfs in this particular case, rather than of neutron stars, which is what we're observing at the moment. So with that, I thank you very, very much for your attention. And the future, I think, for gravitational wave astronomy and transient astronomy in general is very loud and very bright. And I think it's going to be exciting times ahead of us. So thank you very much.
Thank you very much, Dr. Schmidt. For your information, we couldn't actually hear the sounds you were trying to let us hear of the signals in the detector. I suspect that's because of the way you did the screen share. So what was the question again?
The question again was, are gravitational waves propagated as a square law or a proportional?
Do you mean an inverse square law?
Inverse square law.
I think the answer is yes, they are.
Find out at the moment.
No, they're not. So it goes as 1/r. I can hear you again. I don't know what button was pushed, but I can hear you again. No, so strain propagates as 1/r. So that's why it's strain, right? It's not power.
So it's 1/r, not 1/r squared.
Yeah. That's right. So H is proportional to 1/r.
Okay, now we know. Any other questions? At the back left.
Yes, you talked at the beginning about the so-called no-hair theorem of black holes. So you can define a black hole by its mass and by its angular momentum. Let's ignore the charge. When you've got two black holes in close proximity, will they be further defined by the space of gravitational attraction, and therefore you'll get further distortion of, say, the event horizon and the ergosphere?
Sorry, I didn't catch everything.
That was something to do with the no-hair theorem.
I caught the first part, but was it about environmental effects, interactions with environmental, things around it? Did I catch that right?
Yes. So will the ergosphere and the event horizon be further distorted beyond the no-hair theorem by two proximate black holes?
Will the event horizon be further distorted beyond the no-hair theorem by the close proximity of the black holes?
So you're talking about the shape, right? The shape is being distorted, but it's still characterized only by the mass and the spin, right? So you'll see this also when you have simulations of black holes. So, when you have the two black holes, when they're far apart, you have the nicely, either spherical or cylindrical shapes, depending on whether you have a curved black hole or a Schwarzschild black hole. But as they get closer together, the horizons get distorted into these peanut shapes. But they're still only characterized fundamentally by the mass and the spin, even though you are kind of, it's a flexible surface, so to say, so you're distorting it during this process. And once you have merged and coalesced, then you're going back to the unperturbed, undistorted shape.
Right. My question is, these supermassive black holes in the middle of galaxies that we've been hearing about earlier today, were they formed just by a lot of collisions of the type you've just over time? How are they formed?
It's a good question, and it's an open question, right? So there are different theories of how they have formed, and I think you have experts in the audience, actually, or one of the speakers today is an expert on supermassive black holes and galaxy formation. They could have formed through what we call hierarchical mergers through the history of time, starting from the very early population 3 stars, so the first stars that have been formed and were quite massive and have grown there. But, at the end of the day, it's observations that's going to tell you. And I think the galaxy specialists in the audience probably know much more about this than I do.
Right. Anything else? And another one over here.
Are static black holes theoretical, or do they actually exist? I think they're Schwarzschild black holes. Are they the same thing, static black holes?
Static
do they
black
actually
holes.
exist? Yeah.
Do static black holes exist?
But so mathematically, yes, a Schwarzschild black hole is a static space-time. You're absolutely right. A black hole would be a stationary space-time. So, I mean, in principle, you would expect, they come from the end of the life of stars. So you'll have some residual angular momentum, and angular momentum is a conserved quantity. So generally, you'd expect that they have some small rotation due to their formation process. But when even if you had two Schwarzschild black holes, once you merge them with each other, they will be spinning. They will form a black hole in GR. So I would say it's probably unlikely, given that most objects in the universe have residual rotation based on their formation mechanisms.
Thank you.
Okay, so pretty much everything in the universe spins, I think. Right, it's now time for our tea break. We'll say thank you very much to Dr. Patricia Schmidt for struggling with the limitations of Zoom, but nevertheless giving us an excellent talk about gravitational waves. Thank you again.
Thank you very much. Thank you. Have a nice rest of your day.
And we will start again at 20 to 4. We have here now Dr. Timothy Davis. This is him. He did his PhD at the University of Oxford, working on cold gas in early type galaxies, and he's also worked at the European Southern Observatory in Munich and at the University of Hertfordshire. But currently he is at the Cardiff Hub for Astrophysics Research and Technology, which we've already had a speaker from there today, and that's part of Cardiff University. He studies the gas in galaxies and it's linked to black holes and star formation. And he is here to talk about how to build a galaxy, the processes shaping galaxy evolution across cosmic time. Dr. Davis.
So thank you so much for inviting me along to talk to this meeting. It's really lovely to meet you all and take part in this. So welcome to Cardiff. So today I'm going to be talking, as you've heard, about galaxies. So how do we go from the very early universe right down to the universe that we see around us today? What are the processes that are shaping these building blocks, the galaxies that contain all the stars, all the planets, maybe all the life? How do we go from there to here? That's what we're trying to get at today. So we have to start with the Big Bang. So as Sir Terry Pratchett said, at the beginning there was nothing, and then nothing exploded. Of course, that's a lovely way of putting it, and I don't know of a better one, so I'm just going to stick with that. The Big Bang is the beginning of everything in our universe as we know it. 13.7-ish years ago, our universe started in a singularity, an infinite density and temperature point, and it exploded outwards from there. So the Big Bang really created all of the matter, all of the energy in the universe. So I'm going to go through very briefly some of the phases of this Big Bang that take us to the galaxy evolution era that I'm then going to spend the rest of the talk talking about. So at the very, very beginning, you have this roiling, boiling, incredibly hot, incredibly dense soup of particles. So at that stage, the four fundamental forces that we know of were likely unified into one force. So you have all of the particles are zipping in and out of existence as they interchange between energy and particles and back again. But this doesn't last for very long. You have an era very early on in the universe, 10 to the minus 34 seconds after the Big Bang, of inflation, where the universe goes from something being incredibly tiny to incredibly large quite quickly. And when I say incredibly large, I'm talking maybe only to the size of a football or so. But when you've started off infinitely small, that's a big size jump. So at that stage then, this starts to cool down. So you start to eventually have your components of the matter that we know today starting to cool out of this cosmic soup. So you get quarks forming, the building blocks of the protons and neutrons that we're all made of. So they start to form, very early on, up to about 1 second after the Big Bang, you start to get cool enough to have those building blocks of our universe start to condense out. So after that, you have another 3 minutes or so where the universe is a super hot fog, essentially. All these gas, all these particles, you start to get protons and neutrons forming, electrons. The universe at this stage is completely opaque, so the light cannot escape. Every photon that's emitted is then immediately absorbed by something else. So you have this incredibly hot, cooling, but still warm plasma. And you start to get the first elements starting to form as this expands out and cools enough that you can get stable atoms. You start to get things like deuterium, lithium, helium, not just your hydrogen. And your neutrons start to be bound up in these. Neutrons, if you get one of them on their own, they're actually unstable to radioactive decay. And so if you hadn't formed atoms quite quickly, we would have had no neutrons in the universe. So we'd have been left just with hydrogen. That's not a very fun universe to live in, so I'm pretty glad they did get bound up. So you start to get things like deuterium, where you have a neutron bound up in your hydrogen, you get the lithium and the helium. So these things are formed in what's known as Big Bang nucleosynthesis. So this takes about 7 minutes after the Big Bang until you've really bound up all those neutrons into your atoms. And you can actually estimate that because we know the radioactive decay time of neutrons. It's about 440 seconds is the half-life. And so we know now that the ratio of neutrons to protons is about 1 to 8. So you can actually calculate exactly how long that took. And that is in incredible agreement with the production of these types of elements, which is quite a wonderful thing that we can measure here in the lab and apply to the very, very early universe. So after this, you get the era when these protons, electrons, and neutrons really form into atoms and stop being hot. You start to get the electrons falling in and actually forming neutral atoms for the very first time. And this is incredibly important because once the electrons are bound up in atoms, your photons, your particles of light, no longer get immediately absorbed and re-scattered. So you finally get light starting to propagate through the universe for the very first time. And this actually takes quite a long time. But it creates this, the cosmic microwave background. You've probably all seen this before. This here is the Planck satellite's view of this cosmic microwave background. So these are incredibly small temperature fluctuations. The CMB, as we see it today, is about 2.7 Kelvin in temperature. And these fluctuations are very, very small, something like 10 to the minus 3 on that. But if you get a very, very sensitive thermometer, essentially in space, you can measure these small differences in temperature. And these are the primordial fluctuations of the Big Bang that you're seeing here, writ large on the sky in the form of this background radiation. So at this stage, there's no stars yet. There's no galaxies. There's no planets. All you have is these free-floating gases and light and neutrinos. So the wonderful thing about this background radiation is it allows us to work out exactly what the universe was made of at that time, some 300,000 years after the Big Bang. So you can get an actual measure of the constituent parts of the universe. So these figures are from the latest measurements of this on the whole sky, at least, are from the Planck satellite, which was partially built here in the School of Physics and Astronomy in Cardiff. And what we find is that most of the stuff in the universe is not the stuff that you and I are made of. And that is one of the big puzzles in astrophysics. I'm sure you're all aware of this, the dark sector. The stuff that we're made of, the baryonic matter, is only 4.6% of the universe. And we know this because normal matter interacts with light, and so it clumps differently in the early universe than the other components that don't interact with light. And so they change those patterns of heat and cold on the cosmic microwave background. So we can calculate from that really quite precisely that it's 4.6% normal atoms. Then you've got this dark matter. I'll say more about that in a minute, because that's very important for galaxies. And then this dark energy, this force that is expanding and pulling the universe apart slowly but surely. I'm not going to talk much about that. I'm sure people are very interested in it, but I'm probably not the right person to give you all the details. But it's incredibly important, especially at late times, in how the universe is expanding and evolving. So this really sets the stage for what comes next. So that's the galaxy formation era. That's where I'm going to spend the rest of the talk talking about. We've got hydrogen and helium gas, and that starts to clump together to form gas clouds. And then from there, you start to get stars that form, you start to get galaxies, and we're really in this era when you have things that you can call galaxies. So that's what we're going to talk about for the rest of the talk. So we really need to start, when you talk about galaxies, by talking about dark matter, because it's really the backbone of the universe. It's some sort of material. We know it exists because its signature is there in the cosmic microwave background. It's there in galaxy clusters, holding them together when they should fly apart. It's there in galaxies, holding them together when they should fly apart. So we know that there is some form of matter there, some sort of gravitating matter that is holding the galaxies together. We know quite a bit about its properties as well, from the way that it clumps, for instance. We know it's likely cold. It's not a particle like a neutrino with very little mass, because of the way it clumps. So we can actually set some quite strong constraints on what this stuff might be, but still not know what it is. And obviously there's a Nobel Prize out there waiting for whoever can finally locate really what it is and tell us about it. But we already have some quite good ideas just from observing the way that it interacts gravitationally with other stuff. And this dark matter, it forms the backbone of the universe. So in the background here, I'm showing you a simulation of the universe. So you get a supercomputer and you put in your hypothetical dark matter particle. It doesn't really matter what it is as long as it has properties like it's cold, in this case, and you let it evolve. If you let it evolve for 13.7 billion years, you get this web-like structure we call the cosmic web. The very dense intersections of these webs of dark matter are going to be your galaxy clusters. The smaller blobs along the way, they're going to be your galaxies. And the voids in this web are going to be areas of the universe with very little matter left in them, cosmic voids. So really, this dark matter defines the structure of the universe. And that's one of the ways that we're able to constrain its properties. If this dark matter particle was indeed not cold, but hot, then this structure would be much more diffuse, because those particles would flow out away from each other more than they do. And so we can measure the galaxies, the peaks in the density distribution here, and see how they cluster. And so we can tell that this type of structure is how the universe is put together without even knowing what that dark matter particle is, which is pretty cool. So really, because this dark matter only interacts gravitationally, that's what defines the structure of the universe. So this very hot plasma in the Big Bang, the dark matter doesn't care. It doesn't feel heat because it doesn't interact gravitationally. It only interacts gravitationally. So you've got these dark matter particles, whatever they might be, and they're attracted together, and they form this cosmic web, this skeleton. So that's going to set the conditions in which our galaxies are going to have to live. So initially, all of your gas, all of the baryons, you and I, the stuff we're made of, was in a hot gas. So that was a fairly smooth, because it was just sitting there being hot, fairly evenly distributed because it was very warm and didn't fall into the dark matter potential at this stage. But as it starts to cool off, it starts to feel that gravity more because it's not able to zip away with its own kinetic energy. So it starts to cool and condense and fall into the dark matter halos. So about 100 million years after the Big Bang, you're likely to have the first star switching on when you get gas cold and dense enough at the bottom of one of these deep potential wells of dark matter. We would love to see those first stars. At the moment, we can't because of the extreme distance, it's a long time ago. The light from them will have been red-shifted right into the infrared. The James Webb Space Telescope is hoping to help us with that. We're not there quite yet, but hopefully we will be soon. But these first stars herald the era of the galaxies because they're the first ones. And so that's where our galaxy story begins, with the birth of the very first stars. So our best look at the very early universe is here. So I'm showing you here, these are James Webb Space Telescope images of patches of the sky that if you observed with basically any telescope that you have down here on the Earth, they would look completely blank patches of sky, most of them. Few of the foreground stars you would see, of course. And James Webb stared at these patches of sky here. I think this is at least 12 hours per patch of sky here, with this 6-meter dish right the way out at the second Lagrange point, the most sensitive thing we've sent out to space so far. And you see there's galaxies literally everywhere in these dark patches of sky. And in this patch of sky up here, this square, see we zoom in, and we zoom in again, and this is our most distant galaxy that we know of. It's at a redshift of 14.3, which is 290 million years after the Big Bang. So the first stars only formed about 190 million years before this. And it's just this little splurge here. And that's called Maisie's galaxy, after the child of the astronomer who discovered it. I'm sure she's pretty happy to have the earliest galaxy named after her. You'll probably have heard in the news there were stories of galaxies right the way out to a redshift 20 or something, but none of those have proved to be correct. The media, as always, loves to sensationalize these things, and so this galaxy is actually confirmed to be at that redshift. It's really there, and so it's really our record holder at the moment. So that's where we can begin with our observational picture of galaxies right now. We'd love to push it back further, and I'm sure James Webb will do that, but this is where we have to start for now. So I'm going to talk to you a little bit about what makes up a galaxy. So the most important component of a galaxy, at least by mass, is the dark matter. The dark matter dominates the total mass of the system. We know that because it actually holds it together. If you look in its outer parts, it's rotating much too fast. And if there was no dark matter there, those stars would fly away. And they don't. The gas there would fly away. It doesn't. So we know there is a lot of dark matter there. And it's in some sort of quasi-spheric... Oh, it's flickering on the screen there. It doesn't do that on mine. So we know that that dark matter halo is there and it's very, very important. It's typically quasi-spherical, and that's where the galaxy is going to live, right in the middle down there. So the next most important component, at least galaxies around us today, is the stars. So typically around 1,000 to 10,000 times less massive than the dark matter halo if you go out to large radius and add up all the mass. But obviously that's the stuff that we care about. Often we're looking at that light when we use our telescopes. And so the stars are very crucial. And they typically, this here is the stellar disk. These stars form in a disk because of angular momentum. You've heard about it a lot today. It's super important in astrophysics. When the gas fell in to form this galaxy, it had some net angular momentum, and so it has to form into a disk. And so almost all the stars that exist in the universe formed within a disk originally. Whether they now live in a disk, well, that depends on what happens to the galaxy, and that's what we're going to talk about. Some stars have been disrupted from a disk. They live in the bulge in the center of the galaxy. Some galaxies have no bulge, some galaxies are only bulge. And exactly what happens to make that happen, well, that's all the rest of this talk, essentially. Then you have the gas. The gas is very, very important because it's the fuel for future star formation. So you do have hot gas that suffuses the whole of this dark matter halo. If you've got gas that you see with an X-ray telescope at 1 million degrees Kelvin, for instance, then it's not going to sit in a nice disk anymore because it's so hot it doesn't have to, and it's going to basically fill the volume. But as soon as your gas gets cold, so you're talking 100,000 Kelvin downwards to 10 Kelvin, the coldest gases that we typically are able to see in the universe, then they live in the disk. And that disk is usually thin and lives in the center of the potential there. And often it can extend well out beyond the actual stars. You have the black hole. The black hole is actually, as you heard earlier from Mark, completely unimportant gravitationally. The sphere of influence, the area that this black hole can actually affect gravitationally, certainly in our own Milky Way, is about a parsec. Even in M87, this massive elliptical galaxy that you heard about in Mark's talk, it's only a few tens of parsecs that it affects. So really, it's unimportant on that scale, but as you saw in Mark's talk, it can have bigger effects, and we'll talk about those again a little bit, although I won't dwell on them because Mark already did. So that is our galaxy anatomy. That's what we have to work with, and these components will all change in their importance throughout the universe. At the beginning, the dark matter is there and the gas is there, but there's very few stars. As the universe evolves, more and more of that gas is going to turn into stars, and you're going to become stellar mass dominated. So these components are going to be very, very important. So how do we actually study galaxies and their evolution? We want to know how they came into being and how they got from this blob of Maisie's galaxy at high redshift right down to the day we live in today and the galaxies we can observe. So one way, obviously, is use telescopes. So this, for instance, James Webb Space Telescope, we already saw an image from that. That's operating in the infrared. We have optical telescopes here on Earth that can see through the atmosphere like the ones that you all use, just maybe a little bit larger. Things like the Very Large Telescope and in the next generation, the Extremely Large Telescope. As astronomers are very good at naming things, but those all allow us to see in sort of the infrared and the optical wavelengths. But you don't actually have to stop there. As you saw in some of the earlier talks, essentially every wavelength of light contains information about the cosmos that we want to get at. So what I use often are these sort of, people think of them as radio dishes. They're actually observing in the millimeter here in this case. But you can use this sort of radio, millimeter light to shed light on the cold universe or the very hot universe. They often shine in the same ways. So those are very important as well. And you get things like X-ray telescopes that you already saw a bit from that have to be above the Earth's atmosphere, of course. But those are very important in studying the very, very hot gases. But the other way you can do it is by using computers. There are so many processes in astrophysics that are chaotic. The range of scales we have to deal with is everything from an individual atom and its interaction with the next one, right the way up to the size of the universe. So you've got something like 10 to the 40 in scales there, difference between the smallest and the largest. And there's absolutely no way that any observation we can take can constrain information on those scales. It's just not possible. And so we have to try and use our best information about the universe and put this into a computer and let that take some of the strain for us. That's really helpful because so much of what happens is chaotic. We don't understand how to do things like simple, when you stir your coffee, the turbulence in your coffee, we cannot predict with physics. We know the equations that govern it, but we don't know the solutions to those, the Navier-Stokes equations. Again, there's probably a Nobel Prize for someone who solves those. There's certainly a Frontiers Prize, so there's 100K just sat there if you can solve those, so go for it. But computers can solve those for you analytically, and so those sort of fluids are very important. We're talking about gases on large scales in the cosmos, that chaos that we can't capture in equations, and computers can help us solve those. And so I'm going to show you some movies throughout the talk that computers have made and show how they can help us understand some of these problems. So if we take some of these observations, so these here are from the Hubble Space Telescope. These are some high redshift galaxies, so some galaxies at the very early ages of the universe. And you can see they don't really look like galaxies that we see around us today. They're often very, very clumpy. That we think means that they're very, very turbulent. They're not nicely formed disks in the most cases, although there are definitely disks there underlying. They're often very, very small. It's not just that they're far away. They're also physically smaller than the galaxies that we see around us today. So something has happened to them in the meantime. They're typically very, very actively forming stars. Of course, that makes sense. There's a lot of gas in the early universe and not a lot of stars yet, and we need to convert all that gas into stars to get to where we are. And so really what I'm trying to do is say, how do they get from this state to today? What processes are going to be important in that? So what we're trying to do is get from Maisie's galaxy on the left to this sort of galaxy zoo that you've all probably seen in your telescopes, beautiful spirals. Here on the right-hand side of this classic Hubble tuning fork diagram, your lenticulars, so galaxies that still have disks but are quite red and don't have the spiral structure, right the way to the ellipticals that at least look very round on the sky, don't tend to have a lot of substructure. How do you create this zoo of galaxies from this high redshift one? And how do you move between these sorts of things to those sorts of things that are really the end product of galaxy evolution? So, to do that, I'm going to talk you through some galaxy pathways, so things that can happen to a galaxy during its lifetime to really bring it from that early state, very chaotic, very clumpy, very small, right the way down to those zoo of galaxies you saw there. So we're going to start off with what we call secular evolution. Don't ask me why we call it secular, we just do. It's nothing to do with the church, it just means allow the galaxy to evolve on its own, slowly, naturally. So what does this do? Well, I'm going to show you a movie now. Is it going to start? Not yet. Maybe press that. There we go. So here, what we've done is we've put galaxy evolution into a computer. We've put in all the laws of physics we think we know, the way gas moves, with the way stars form, the way black holes work, the way supernova work, and we try and form a galaxy. So you start off here, you see in the bottom left-hand corner, you've got the cosmic web, the dark matter. We're zoomed in to the center of this big clump of dark matter here. You're seeing the gas density in the main panel. The stars are down here in this panel. And this is just a zoom in down there as well. And you can see in very early times, everything is very, very chaotic. You've got all of these dark matter substructures, these clumps that are coming in and merging. And they're bringing in lots of gas. But you see now, at about redshift 2, you're really starting to form a fairly stable disk down here in the center as this gas accretes in from the large scales. And this disk is clearly rotating. We're going to stop here and we're going to rotate around the system so you can see it in detail. You see you've already got nice spiral structure. On the left there, you're seeing the metals and how they are distributed, and they're distributed a little differently from the gas density because they have been formed in the stars and flung out into the universe. And then we're going to follow this down here. You see you've got a galaxy merger here. We're going to talk more about those later. This is a fairly small one, so it doesn't affect the galaxy very much. And you can see it's sitting there. This is a zoom in on the central disk. You can see it still forms a very nice disk, basically the whole way through its evolution. We're now getting towards the local universe, and you think things have calmed down for this galaxy. It's evolving fairly secularly, as we would call it. You have a halo of gas around it, which it's slowly accreting from. You can see that those clumps falling in. And you can see very nice spiral down there in the center that could be like our Milky Way when we get to redshift 0. See a low redshift here. When we stop, there is a little galaxy falling in right there at the center. Excuse me. So this was from a simulation called Illustrious TNG, you see here, where we've taken all these processes, put them in this computer. So that's secular evolution. So the main dominant processes here is the gas collapsing to form stars. So you heard Nico's talk earlier. Nicolas told you all about that. That happens. Those stars form, and the massive ones will go on to go supernova. If you're over 8 solar masses, you're more than likely to explode and feed back this massive amount of energy into the interstellar medium around you. That interstellar medium is going to heat up as that shock wave blasts into it. And that means that it's not cold anymore. It's not available for star formation in the recent future. It's going to heat up, it's going to blow out a little bit, and it's going to take time for it to cool back and fall back onto the disk, what we call a galactic fountain. So that slows the star formation. And as that's happening, you get this slow accretion from the surroundings, be that from the intergalactic medium or most likely from the halo around you, so-called the circumgalactic medium, which is the hot gas around galaxies. That's slowly cooling into the systems, providing more fuel for star formation. And in secular evolution, most of the time, that inflow approximately balances your rate of star formation. So what you have is a fairly steady state system that's going to continue forming stars fairly regularly at a fairly constant rate throughout the life of the universe. So that's likely going to give you at the end a spiral galaxy. And Anna will tell you all about that in the next talk, how that all works and the processes that go on within a spiral galaxy itself. So if you want to go from Maisie's galaxy to a galaxy that is fairly regular spiral, they're probably going to be dominated by these secular evolution processes, slow, regular, steady. But not all galaxies are like that. So how do we then go from there to the more elliptical, the red things, the dead things? That's going to require much more. So one thing that you can do, we already talked a little bit about it, is galaxy mergers. So if you slam two or more galaxies together, then you're clearly going to have a big effect on those systems. And we think this process should be incredibly important because the universe is hierarchical. We have many small things at high redshift, and we want to make big things at low redshift. Excuse me. After the pandemic, you get so used to talking to your screen that when you talk to a big audience, it's... So we think the universe is hierarchical, so this merger process should be incredibly important. So I'm going to show you now another nice simulation. We all love movies. Here we've done exactly the same thing. We've put the physics into the computer. We've set up two galaxies now. We're not trying to do all of cosmology here. We just set up two isolated galaxies. And we're going to let them merge. So you see they have their first passage. Now they're on the death spiral in towards each other. They're going to smash together. And you see you no longer have a nice disk galaxy anymore. You've randomized the orbits of your stars, and you've flung a lot of your gas out and consumed it. So now, at the end of the simulation, a few billion years later, you have something that looks fairly elliptical. It's got a star-forming disk in the center of this one, which we observe maybe 25% of the time. That was work that I did during my thesis. But you see there, you've turned two spiral galaxies into an elliptical galaxy through their merger. Now, this doesn't always happen. If you slam galaxies together in different orientations, you can have different things happen. So if they're both rotating in the same direction, for instance, you slam them together, often you end up with a disk at the end as well, because you've got so much angular momentum in the system, you keep a disk. If you have galaxies that are polar, often then the angular momentum, you just build a bulge, but you don't actually destroy the disk at all. So this process is stochastic, it's random. But luckily, because we have this hierarchical universe, the average galaxy has gone through these sort of major collisions approximately 2 times during its lifetime. The average galaxy has. And it's had many smaller things happen to it too, small dwarf galaxies falling in, for instance, bombarding it from different directions. And they can all help build these sort of more red and dead, the elliptical and lenticular galaxies that you see, through these combinations of different types of mergers. So the important physical processes that are going on in these is collisions. So the gas in your galaxies, that's a collisional, it's fluid. It fills the space available to it. And so when you slam those galaxies together, that gas is going to collide and it's going to shock. And when it shocks, it loses angular momentum and it's going to fall into the center of the system. Suddenly, you've gone from having, maybe 1,000 solar masses per square parsec in the center of your galaxy, it's a fairly normal galaxy, to 10 to the 4 solar masses per square parsec in the center of your galaxy. You're going to have a burst of star formation. The stars are going to form there like the crackers. And you're going to have what we call a starburst. So here's an example of a starburst. This is a new James Webb image in a composite with Hubble here. This is the galaxy ARC 220. It is a big cosmic smash-up of 2 very gas-rich galaxies. And you're seeing here a fairly elliptical morphology, although it's quite disturbed, and you still see these big arcs and features, umbrellas, we call them. And in the red, you see the dust, the hot dust that is in these star-forming regions at the center of this galaxy that is really, really forming stars at a rate of 1,000 solar masses a year or something, compared to our own galaxy that's forming 1 solar mass a year. So this is a very extreme thing that happens in the middle of these galaxies when they merge, if their gas collides. So that's very important because that uses up a lot of this gas very, very quickly. If you look at the Milky Way, for instance, at 1 solar mass a year, and it has about 1 billion solar masses of gas. So it will take 1 billion years to use all that gas up. And you have all that cooling out of the halo, and that's coming in at approximately 1 solar mass a year. So it's all going to balance. You're going to form stars at approximately 1 solar mass a year for the rest of time until that halo is depleted. In this case, you've used up all that gas in only 100,000 years. There is no way you can fuel that back up again at that rate. It's just not possible. So you're going to deplete that gas, and you're going to form a red and dead galaxy at the end of this. The other important thing that happens in the mergers is the stars, they don't collide. Stars, although we think of them as very big compared to the Earth, they're tiny, tiny, tiny on the scales of a galaxy. So you don't actually really get stellar mergers when you collide galaxies. We shouldn't be too worried when Andromeda collides with us. Nothing's going to hit the Earth. The Earth is going to be fine. There's a very, very tiny possibility a star comes close enough to fling us off, but the probability of that is about 1 in a billion. So if any of us are alive by then, we shouldn't worry about that. We should enjoy the fireworks. But what will happen is the star's orbits will be perturbed. So you no longer have nice disk orbits, but you throw stars' orbits up into the plane, and so you build a big bulge in your system quite often. So that is a very, very important effect of mergers and how we think the majority of at least the classical sort of round bulges are formed. So this starburst, once it's depleted all your gas, the galaxy is going to fade, it's become elliptical. So you're going to end up with this red lenticular elliptical galaxy after this. If your single merger doesn't do it, then you have to wait for your next one, or maybe your next one, or maybe one of these other processes that I'm going to talk about. These mergers are very important. So moving on then, we already heard a bit about this, so I'm not going to spend too much time on it, other than it's actually an area that I work in, so I'm going to try and show you some of my own work as well. Active accretion onto black holes. We've heard about it already. I'm going to show you now another merger simulation of 2 merging galaxies. I'll start it in a moment. But this time, we allow their black holes to turn on. If gas gets close enough, then it will accrete onto that black hole, and that will provide energy into the system. You'll see a very, very different... Work for me. Go on. Yes. OK. So you see, again, we've got 2 spiral galaxies. They're now merging. The gas is being disrupted. And you'll see in a minute, the torque is going to bring gas close enough to the center that are losing enough angular momentum to fall onto that black hole. You start to see the red material, the hot material. That's the black hole turning on. And in a moment, you'll see it really start to go. And it's starting to blow these galaxies apart. Their gas is completely shredded by these black holes that turn on. And you end up with something that looks very, very different from the merger remnant that you saw in the previous video. Here you see the black holes are going to merge and go completely crazy and blow out the last remnants. So you're left with a galaxy with very, very little gas in this case. So mergers are an important way that you could fuel these black holes. They're not the only way. You saw in Mark's talk, you can fuel those just in disks, for instance. It's worth remembering, though, that black holes are not hoovers. They do not hoover up material. All they do is sit there, and if material happens to fall on them, brilliant. But you can't force that process very easily. If you imagine you've got the Earth rotating around, we're 8 kiloparsecs from the center of the Milky Way, and the black hole itself is smaller than our solar system. So you have to lose 99.9999999% of your angular momentum to allow you to fall onto that black hole to a region where the strong gravity can actually cause you to eventually fall in. So it's quite hard to do this. Mergers is one way you can do that. We know that spiral features that Anna's going to talk about will do this, for instance. But it's actually quite hard to turn these things on, but they do seem to be turned on. And they do seem to do things to galaxies. So that is what Mark already told us about: winds, jets, heating and expelling gas. And these things are likely to play key roles in forming these lenticular and elliptical galaxies. So why do we think that? Well, here we're going to start off with the galaxy luminosity function. So what this shows is the density of galaxies in the universe on the y-axis. It doesn't matter about the exact units. And then the galaxy luminosity on the x-axis here. So the very brightest galaxies are quite rare, and the very dimmest galaxies are quite common. That makes sense. But if we just took the way that dark matter clumps together, the distribution of masses of dark matter, in our simulations, remember, we think we know what the properties are that matter because we can measure this clustering and we can measure the CMB. We've got all these different measurements that tell us this is how it should cluster. And you can see the red line is not the same as the blue observations. You've got very many fewer massive galaxies, and you've got very many fewer small galaxies as well. So this is a real problem. Why are we not having the cosmic fraction of stars in each dark matter halo? Well, you can kind of guess the answer. At high masses, we think that this is done by the black holes. The AGN in the centers have to turn on, and they blow out all that gas. Mark already told you that we stop these very massive galaxies forming by turning on these black holes. That's very important. But at low masses, these small dwarf galaxies typically don't have active supermassive black holes yet. And so what's going on there? Well, it turns out you don't actually need them. If you're a very, very low mass galaxy, it doesn't take very much to remove gas from you. You only have to move at, let's say, 100 kilometers a second to escape a very small dwarf, whereas up here you might have to move at 500 kilometers a second, much, much higher. And so actually at low masses, all you need is supernova. If a cluster of supernova go off in your dwarf galaxy, they're enough to completely blow your gas away. So they suppress the formation of those dwarf galaxies. And we only need the black holes to do the very massive galaxies. If they are there at low masses, they don't seem to be very important because the supernova do everything we think we need. So, a little bit of an aside onto my research. A lot of what I do these days is looking at how these black holes affect galaxies. So how we go from a star-forming galaxy, how does the black hole then transition it, do this process of blowing out that we talked about, when it's so very, very small and unimportant in mass and in gravitational radii. So you already saw a version of this plot. Here I'm showing you the masses of black holes on the y-axis against the stellar velocity dispersion, so how random the motions are in the centers of the bulge. So that's just a measure of the bulge mass that you saw in Mark's plot. So this plot has a few more galaxies on it. It's much more recent. This is a 2009 paper by McConnell and Marr. And you can see that we have this very, very strong relation between the mass of this bulge, if you want, on this x-axis, and the black hole mass. So somehow these very tiny black holes know about the galaxy on large scales, and vice versa. And so we think that has to happen by this co-evolution process that Mark talked about, where you accrete some gas, the black hole then blows out, suppresses star formation in the galaxy, and then you get a cycle of that. So you end up with this black hole acting as a valve at the center, regulating the growth of your galaxy somehow. So if that's true, and if you want black holes to be the ones that quench the massive galaxies, so remove all the gas and get rid of the star formation, then you would hope that at fixed bulge mass here on the x-axis, the quenched galaxies who don't have stars forming anymore should have bigger black holes. That makes sense. They've done more work. They've accreted more gas in order to do that blowing out. So this was one of the first studies to really attempt to do this. So the blue points here are spiral star-forming galaxies. And the red and green here are quenched early types, ellipticals and lenticulars. And the red line is the best fit to the red points, and the blue line is the best fit to the blue points. And you can see they are offset from one another. But you also see that the scatter is very large compared to the offset between these. And actually, the way we measure these black hole masses is typically different in these different populations. We're typically using the gas in the late-type galaxies, and we're typically using the motions of stars in the elliptical galaxies. So that's a problem, because you end up with an offset because your measurement wasn't good enough, not because of real physics. So what I do is use the masses of supermassive black holes to measure. We use the gas rotating around them, the cold molecular gas, to measure this. I realize I've been too slow. I'll speed up. So This is an example. This is a big elliptical galaxy there, NGC 383. So if you look down in its center, it has this disk of gas. And as I say, a lot of elliptical galaxies actually have this if you look close enough. This clearly has a black hole because you see the base of a big jet here coming out in X-rays. So it was observed with this Plateau de Boer interferometer that's in the French Alps a long time ago, back in 2010. And you see that there's this disk of gas also in molecular gas. So you're seeing here the carbon monoxide molecule here in this galaxy, 66 megaparsecs away. So what we did is we went to ALMA, this interferometer in Chile, and observed this same system, but with much, much higher resolution. So our observations here have about 40 parsec resolution in this galaxy far, far away. You see the big improvement in this beautiful disk. And actually, if you look at the kinematics, so here I'm showing you an image of the velocity of the gas, where red is red-shifted, blue is blue-shifted, green is not moving towards or away from us. And you can see the beautiful rotation pattern, red on one side, blue on the other. And the very, very center of the galaxy, the gas is moving fast. That already tells you there's a black hole there. But you can sort of extract that a little bit better. You see the rotation of the gas as you go from the outside. It's essentially flat, there's dark matter there. And then as you come towards the center, the velocity increases massively. And that's the gas spinning faster and faster and faster as it gets closer and closer to that black hole. So you can use that to measure. You can fit with a model. And that gives you 3 billion solar mass black hole in the center of this galaxy, for instance, that we were able to measure for the first time using this technique. So we've been able to measure now a lot of systems. So all the red and blue points here are our measurements using this technique. So we're really starting to add to this knowledge of supermassive black hole galaxy coevolution there. So finally, I want to talk about environment, because that's the other key thing that can happen to galaxies, is you throw them into an environment where there are lots of other galaxies, and that will change its evolution quite substantially. So this is an example here. This is a Hubble Space Telescope image here of a dense cluster. You see there's many, many, many galaxies, all in the same big dark matter halo now. We're talking about 10 to the 15 solar masses of dark matter here, with 10 to the 13 solar masses of galaxies rotating around. There's often a giant elliptical in the middle. You see these features that are actually gravitationally lensed objects that I'm not going to talk about in the outer parts. But so it's a dense environment, and dense environments can do a lot of stuff to galaxies. So the first one of these things is ram pressure stripping. So this is like if you stick your head out of your car window as you're going along the motorway, you feel this massive force pushing you back. Your hair will stream out behind you. Now imagine you're a galaxy, and you've got a lot of gas in you. This gas fills the space available, so it's got a lot of surface area. And so when you meet a gas going the other direction, like the air on the motorway, you're going to be pushed backwards and out of your galaxy. So you can see an example of this here. Hopefully it starts. It doesn't want to play. Okay. If this movie was playing, you would see, oh, there we go. There we go. Yes. Okay. You see that this disk is falling into the galaxy cluster. The hot X-ray plasma is pushing on the disk, and you're creating this big wake behind you. This is ram pressure stripping, and it's going to push the gas out of your galaxy. And if you've not got any gas anymore, you're not going to form any stars, and you're going to become red and dead, maybe a lenticular galaxy. YouTube. Stop it. Sorry. There we go. Okay. And this is a Hubble Space Telescope image of exactly this happening in a galaxy. This one, I believe, is in the Virgo cluster. You see the galaxy here in the white colors, the stars, and then you see the dust in the very, very center being blown out, and then all this new star formation that's forming in this wake behind the galaxy as this gas is compressed, it forms some stars, and then it blows itself away and is gone forever. So these stars are going to join the intercluster medium. They're just going to be floating around in this galaxy cluster, not in a galaxy at all. And this galaxy is going to lose all its gas. It's going to transform. Tidal stripping is very important too. That's where you get another galaxy and you pass it close by your galaxy. You don't actually merge, because in the cluster, your galaxies are moving very fast with respect to each other, so they're unlikely to merge. But they will pass quite close. So the gravity of one might pull the gas out of a smaller system and get rid of it. So there are many examples here. Some of these are mergers, but some of these are just things passing by each other. You see the blue is the gas being pulled way out of the galaxy. For instance, this system here, there's all this gas out here that's basically not in the galaxy at all. It's just been pulled away in this system. This actually is one of the systems with a brilliant JWST image from the first release. That is very, very well studied. But these tidal effects can pull gas out of galaxies. The final one is starvation. So you have this halo of gas around galaxies, and that gas can be easily pushed away by ram pressure stripping. And once you no longer have that halo of gas around the system, it can't cool down onto your galaxy anymore. So you're only left with the gas in the disk that will form stars, but be depleted. And so it will starve. So for my research, I do actually study this, and I'll go very, very quickly over this. We find these sort of ram pressure stripped tails in the cold gas, pushed out of galaxies, at least at low mass, not so much at high mass, it turns out. These systems are more normal, and so might be more strangled rather than being directly stripped. And it seems to be pushing gas to be more compact in the galaxies rather than actually being removed totally. It still sits there, it still forms stars, so it's probably quite a slow process, this environmental process that strips galaxies, at least in the low redshift universe. So, my final slide, how to build a galaxy? Well, to go from there to here, there are various things you can do. You can do very little, and then you probably end up with a spiral galaxy. You can merge them together. You can feed the black hole, or you can throw it in a cluster or group, and you'll probably end up with more of a lenticular or an elliptical. So I'll leave it there.
Thank you, Tim. I would say you're a natural storyteller, and you also win the prize for the most appropriate T-shirt. But we will have to move on now, and we won't have any questions on that. We don't want to squash Dr. Ana, who is here today. Right. Dr. Ana Duarte Cabral. She did her PhD at the University of Manchester. It doesn't say where you're from initially.
I'm Portuguese.
Portugal, right. She did a PhD at the University of Manchester, and she also worked at the University of Bordeaux, also Exeter, and then Cardiff. She is a Royal Society Research Fellow at the Cardiff Hub for Astrophysics Research and Technology. She works on star formation in spiral galaxies, linking the large-scale dynamics of galaxies to the small-scale physics of the star formation process. So I think this kind of wraps up today, linking what we just heard about galaxies with what we heard right at the beginning about star formation, hopefully. And her talk is entitled From Spiral Galaxies to Stars, the Role of Galactic Dynamics in Shaping the Birth Sites of Stars.
Thanks. Right. So thank you so much for holding on all day and still awake to listen to me. Hopefully I won't put you to sleep. So I'm here to tell you a little bit about what takes a spiral galaxy to form stars. So as was said, I'm trying to link the large scales of a spiral galaxy like our own to the processes that lead to the formation of stars. And in particular, what is it in a big spiral galaxy that shapes these sites where stars are going to be forming? So that's really the question. When you look into a spiral galaxy, how does that galaxy go on to form the stars in it? What is the physics in the large scale that are going to regulate how you convert gas into stars? And actually, if I don't know if Nicolas has talked to you about this a little bit, but if you go from a molecular cloud to a star, typically and historically, we actually think that this is a relatively universal process. And what does that mean? It means that, well, regardless of where you look at, whether it's in our own galaxy, a nearby region, or a faraway one, different masses, you're going to form the same type of stars, and you're going to form them at the same rate. So it's kind of a universal sort of process. And this is really, driven by the fact that we see some observational properties in star-forming regions that seem to be very, very similar, regardless of where you look at. And this is all based on local universe observations. And one of them that is quite key is this one. So this is a plot that shows you on the y-axis, essentially, the amount of star formation that a galaxy has as a function of how much gas it has. So on the x-axis is how much gas does my galaxy have? On the y, how much star formation is going on? And you can see that, so each of these points in this graph is a single galaxy, just averaged out into one single point. And you can see the Milky Way right at the bottom there. And these different colors are just different types of galaxies. And they all seem to follow this nice relationship. So this is a relationship that we call the Schmidt-Kennicott law. We even call it a law. And it is really great. If this is really the case, then that tells us that we can use very simple recipes to apply on these big computational simulations that Tim has showed you that try to reproduce our universe. So these big cosmological simulations, there's no way that they could actually model the star formation at the same time as they model the entire universe, because it's just not feasible. So we need these simple recipes that tell us, well, our galaxy has this amount of gas, so it's going to form these amount of stars. This is great, but the story is not that simple. Because when you actually look at a galaxy in detail, and you look at the star formation that is going on in different parts of the galaxy, these relationships then break. You don't have a nice, tight correlation. You then have a huge scatter of several orders of magnitude. And so what is it that drives this scatter? Can we learn some of the physics by looking at what different parts of the galaxy are doing to the gas? And so we really need to start looking at galaxies as these star formation engines. So on the talk this morning, Nicolas has told you all about how you go from a molecular cloud and you form your stars. So looked at the small scale process of star formation for the little ones, for the big stars. And what I'm going to tell you about is how you go then from a galaxy to form molecular clouds. And maybe some hints into what a galaxy actually does to the molecular clouds that may or may not affect how star formation then goes on in those clouds. But this is really not a simple job. So we're full of limitations and limitations and limitations to what we can do. And if we start with observations of our galaxy, we all know we live in a spiral galaxy, so if we could look at our galaxy from the top down, that would be more or less how we think we should look like. But in reality, we can't see our galaxy with that perspective. Right? We are right in the middle of the galactic plane of our nice spiral galaxy, and so all we can see really is a stripe across our sky. So all of the gas clouds in our galaxy are just lined up, all ones in front of the others. It's really, really hard to actually tell where a specific cloud that we can see in a lot of detail, it's really hard to place it in the 3D context of the galaxy. So we have this problem of edge-on perspective. We're right in the disk, we're looking edge-on through the disk. And in fact, when we look at the night sky and we see our Milky Way across, we're really only seeing our clouds in 2D, so projected onto our sky. And we have absolutely no information about their depth for most of them. They also don't move, so they're kind of frozen in time, so we can't see how they move around in the sky. They're frozen. But we do have a little thing that gives us an insight into their 3D distribution. And that's if we can look at the molecular line emission, we know the specific frequency of a specific molecule that is emitting inside these clouds, and we can use the Doppler shift to tell us whether this cloud is moving towards us or away from us. So that gives us that third dimension. It's not space, but it's velocity. So we usually have these cubes of data, so 3D data sets, but they're basically position, position, and then velocity. So really, when we are an observer of our Milky Way, our galaxy looks like this. So this does not resemble anything like a spiral. If you were expecting to see a nice little spiral pattern there, but this is essentially on the x-axis. It's the angle of you looking around the galaxy, around yourself, and looking around the galactic plane. So 0 there in the center is if you're looking at the galactic center. And then on the y direction, you have the velocities. Stuff which is at negative velocity, so at the bottom of this images is things coming towards you, and then on the other side you have things going away from you. And so actually you can tell how our galaxy is rotating by looking at this. And actually if you take the position, if you know the rotation of our galaxy, you know the rotation curve, and you have a guess at where the spiral pattern should be, you can then map back where those spirals should be in this kind of images. And so these tracks that you see in colors on top, they're where we think our spiral patterns in our galaxy are. So we can kind of reconstruct the 3D image of our galaxy through that. But you can also see that, for example, in these areas here, you have quite a lot of spirals, or spiral tracks, that essentially are in the same place in that plot. So if you observe a cloud in that region, you have no clue whether that cloud is in the Perseus arm or in the Scutum Centaurus or even between the arms, because they all fall in the same velocities. So you have no way of actually telling whether a cloud is in an arm or in the spiral arm or in an interarm. So it makes it really, really hard to infer what the environment is doing to these clouds. So you could say, okay, let's go to a nearby galaxy. A nearby galaxy, we can see the environment, so we can do this. So this is an image of NGC 628, one of the galaxies observed recently with the ALMA interferometry, the team also mentioned. And so in here you see in blue is the stars of the galaxy, and then in red you have the distribution of the molecular gas, so the gas that is going to go and form stars. But the problem is, even with the best interferometers and observatories that we have in the world, we lack the resolution to actually go inside these clouds and see what's happening in terms of star formation, embedded star formation. And so this survey, for example, is one of the best ones that is out there. And it resolves 1 arcsecond, which is amazing. But because these galaxies are so far away, that corresponds to about 100 parsec scales, or a few tens. And really, when you compare it to what Nicolas has told you this morning about star formation, this falls a little bit short of what we would need to see what's happening inside the clouds. So just to give you an idea of these scales, if you take one little region in that is about the resolution element of this survey, so around 100 parsecs, the kind of regions that Nicolas has showed you this morning are about that size. And so you can see what we could expect to see inside of that cloud is a lot of little cores where you form individual stars, you have feedback regions, you have all sorts of things happening we just can't see with the nearby galaxy observations because they're just so far away. And then you could go, okay, never mind the nearby galaxies, let's go into models. We have high performance computing, we can do this. It's actually also very challenging because of the range of orders of magnitude in densities and in sizes, and even in the physics that you need to put into these models to actually model properly everything that goes inside a molecular cloud. It just makes it super complicated and prohibitive even to actually do this consistently. So what people have been trying to do is to go around the problem and do the best we can. And that is, for example, you run a simulation of an entire galaxy where your resolution is not that big, so you can sort of model what the ISM is doing, so you have some feedback, you have spiral arms, You have some chemistry that allow you to form molecular gas. But then you don't actually study star formation there. You take those simulations to then zoom in and do higher resolution simulations on just a small portion of that one. And then you can do that again, increase the physics, increase the resolution, and try to go down to a cloud scale and see what it's doing in terms of star formation inside of it. But the thing is, you can only do that for a handful of clouds across your galaxy. So if you're trying to really see what the galaxy does to the clouds, you can't just do it on 5, because that's not statistically significant. So it's still, we're getting there, but it's still a big, big challenge to actually do the whole process self-consistently. So indeed, the impact of galactic environment on star formation, on properties of clouds, is still unclear. But if that were it, that's it, my talk's done, I can go. But no, we're limited, but we're actually not blind. We're quite ingenious in trying to find ways to try and quantify what a galaxy is doing. And so I'm going to take you through what we know so far about the processes that a spiral galaxy has, and how we've tried to look into how they may or may not affect what's happening into clouds. So this is going to be essentially what my talk's going to be about, galactic dynamics in a spiral galaxy. So if you look at the background image, which is M51, you can tell it's a nice, big, grand design type of galaxy. And just by looking at this image, you can almost feel that this is a dynamic system, right? You cannot form static spirals, right? You can feel that it's rotating, it's doing all sorts of things. You can see the spiral arms with lots of these red regions, which are where you have the star formation. You can see the dark lanes of dust where star formation is occurring. So it feels like a very dynamical place. And there's a lot of things that happen that could regulate how star formation happens. And so some of the things that I'm going to be highlighting today, this is by no means all that is happening on a spiral galaxy, but is maybe some of the more interesting things that I thought could be playing a role. So I'm going to be looking into mid-plane pressure, shear, streaming motions, and maybe then how that affects the spiral arms, the gas in the spiral arms, the gas in the bars, and gas in galactic centers. So if I start with the mid-plane pressure, what is this? So as Tim said, most early galaxies, as soon as you have some angular momentum, you're going to fall into a disk. So all of these spiral galaxies are disk galaxies. So if you're looking at them edge on, you see this, you might have a little bulge at the center, and then you have a nice disk of stars and gas. So this mid-plane pressure is just essentially the weight or the pressure that the gas feels because of the weight of the stars and gas onto the mid-plane of the galaxy. And it has been suggested that this mid-plane pressure would actually regulate the transition of diffuse atomic medium into a molecular gas. And you need the molecular gas, you need the dense stuff to form stars. So it could be that the very shape of your galaxy is going to be the thing that's regulating that transition. And this is an example of one of the nearby galaxies. This is seen in the optical, so you can see the stars where they're distributed. So you see kind of a bulge in the center, you see the spiral pattern. If you look at this galaxy using gas, it's going to look very different. So if we look first at the atomic phase, so the warm and diffuse medium, this galaxy looks like this. So this is the emission from atomic hydrogen, and you can barely tell that this is the same galaxy at all. And it's the same scales. This is not showing you different things. This is, if I could put it on top, you'd see. So actually, you can barely recognize any spiral pattern on the image at the bottom. You can see that you have H1 emission, so atomic hydrogen emission, that goes way beyond the part where you see your stars. And then when you look at the molecular gas, so the gas that will go on to form stars, it's actually very different again. So this time is now concentrated in the central part of the galaxy, is concentrated where the spiral arms are, which goes in line with what you expect from this mid-plane pressure thing. So that's where you have most of your stars. That's where that pressure would be higher. So maybe it is regulating how you go from a diffuse medium into that atomic one, into the molecular one. However, for you to go from diffuse atomic gas to dense molecular gas, all you really need is something that makes your gas compress. So, yes, you just need some form of compression. Midplane pressure is not the only thing in a spiral galaxy that can provide that. And if I show you this simulation of a spiral galaxy evolving, you can see that there's a lot going on that can provide this compression of material. So in this image, you have in the grayscale the atomic gas, and then in color is everything that is molecular. And you can see all sorts of things happening. So you have cloud collisions, you have supernova explosions that sort of create these bubbles and push gas away, and that gas is going to shock another gas. So that's going to create, again, a density increase. You also have the material as it crosses or goes through a spiral potential, it compresses that gas, and therefore you form the molecular gas there. And it's really, really hard to actually try and separate what does what, because everything is happening at the same time. So you might have higher midplane pressure, but you also have all these other shocks that happen for other reasons. Now, when you look at this simulation, and there's one thing that you might notice, which is that the gas at the center is rotating at higher velocities, angular velocities, than the gas in the outskirts. And this is because of the gas having a differential rotation. So you have a flat rotation curve, linear velocities of the gas are the same, which means that gas closer to the center is actually rotating with higher velocity around the center. So there's something that this differential rotation induces, which is shear. And so what shear does, essentially, if you have that parcel of gas going around the galaxy, the part that is closer to the galactic center is traveling faster than the part that is further away, and that's just going to stretch your cloud out. And in this simulation, you can't really see that very well. You can kind of see it because it has feedback, and so there's all these other things going on. But if you use a simulation that doesn't have feedback, you can see that a lot more clearly, the effect of feedback in stretching the gas into these long, thin sort of stripes. These are numerical models. So how does it look like in observations? Do we see this? Yes, it stretches clouds. It creates what we've called first feathers in nearby galaxies, which are sort of these little plumes of material that go off the spiral arms, and they're stretched out into these interarm regions, and we think they're because of that shear. In our galaxy, we haven't called them feathers, we've called them giant filaments. And so we see these as well. This is one of the longest filaments we've seen in our galaxy, is more than 100 parsec long. We called it the Nessie because it goes like a wave. So we've seen these things. Okay, so the shear in a galaxy is able to change the morphology of a cloud, but does it actually do anything to the star formation? So people have tried looking into this by looking at something that we call the Thom-Rique parameter. So I'm not going to go into details about what that is, but it essentially is trying to look at how strong the shear is compared to the gravitational field of your cloud and see whether or not the shear can provide some support against gravity. Because the shear acts in such a way that it stretches your cloud as it rotates around the galaxy, it provides actually this rotational support of the cloud. So it could be that if the gravity of the cloud is not enough to counteract that shear, the shear could actually stop that cloud from collapsing or slow it down. So this parameter here quantifies that. So essentially, for very large values of this Thom-Rique parameter, shear is able to stop or to support the cloud against gravitational collapse, while below that, it's just not enough to do anything to the cloud. So what's happening in a galaxy like M51, here you have the arms in these black lines overlaid on top of this Thom-Rique parameter, and the interarms, because these are regions that are shear dominated. So the shear is strongest in the interarms. And also because the gas is relatively diffuse over here, it means that we essentially get large storm Q parameters. So clouds in the interarms, they can be slowed down in their collapse because of this shear. So the shear can actually do something to the cloud stability. However, in the spiral arms, because these are regions where the shear is reduced, and they're regions where the gas piles up, and so you actually allow the growth of molecular clouds, so you have more mass, so your gravitational potential is strongest in these clouds, actually gives you very small Tomry Q parameters. So in a spiral arm, the shear is just not enough to do anything to the cloud stability. There might be other things to do, but the shear is not playing a key role. But you might ask, but so why are spiral arms regions of reduced shear compared to the interarms? If your gas is rotating always with the same velocity as it goes around the galaxy, there's no reason why a spiral arm at the same radii would feel a different shear than an interarm region. Why is it that it's reduced shear? So this brings me to something that we call streaming motions. So streaming motion, what is this? It's essentially the acceleration that the gas feels as it approaches the bottom of the potential well. So as it's being pulled to the bottom of the potential well. So if you can imagine the gravitational potential of your galaxy, you have the stars in the bulge, you have more stars in the spiral arms, so the potential is strongest in these regions where you have more mass. And so if you could map that out into like a 2D curve of how this potential looks like, it's actually full of like hills and, well, mountains and valleys that the gas has to travel through as it goes around its nice little circular orbit around the galactic center. So it's not a flat surface. The gas actually has to climb that potential, then go down the potential, climb the potential, go down. And so as it climbs the potential, it feels an acceleration backwards into the previous valley that it passed. So it slows down the motion. And then as it then passes the top and comes back down, it then starts to feel an acceleration on the opposite direction, trying to pull it to the bottom of the potential well, and it accelerates that velocity again. So it feels this streaming motion, this acceleration and slowing down of the motion. And this is what means that when the gas reaches the bottom of the potential well, so when it reaches that spiral arm, it has kind of not quite got the velocity of the arm, but quite close to it. So it feels less of a shear as it does so. So how big are these streaming motions? Well, they can provide velocity deviations quite large, from about 5 to even 25, even more, 30 kilometers per second. In our own galaxy, for example, with recent Gaia results, we've been able to measure these variations in the velocity of the stars in the neighborhood of the sun. And so this is about 3 kiloparsecs away from the sun, looking at these variations, and we can see variations in the velocity of about 10 to 20 kilometers per second, which is quite large. In nearby galaxies, this has been done as well. So you have, for example, this galaxy here, where you can then look at the gas emission and look at the velocity of that molecular gas. And then you can fit a model of the rotation curve to that galaxy. You subtract the two, you get a residual. And that residual essentially gives you the deviations from that nice circular rotation. And these residuals can be, again, as big as 20, 30 kilometers per second. And it gives you, and you can tell that they actually match the positions of where the spiral arms are, which tells you that the spiral arms are actually doing something to change the velocities of this gas. Right, so spiral arms are these regions where the gas piles up. So the gas, when it reaches the bottom of the potential well, it gets compressed. It leads to cloud merging, to convergence of flows. So maybe we should be seeing some changes in the properties of clouds that are in these spiral arms. If they're colliding with each other, if they're, being steered up, maybe we should see some signature of this. And people have tried to look at this. Are molecular clouds any different in an arm or outside an arm? And the answer is really unclear. So in nearby galaxies, some studies have found some changes, either in velocity dispersion, so the levels of turbulence, or in the masses of these clouds that are more massive in the arms. Other galaxies, not so clear. And then in our galaxy, it doesn't seem to be any trend, even though it's really, really hard, as I said in the beginning, to actually put the context of these clouds in the 3D space of our galaxy. Even when we do our best to do this in the most unbiased way, we don't see any specific trend. So it makes it really, really hard to understand what's going on. But we should maybe expect different answers depending on what kind of spiral galaxy we're looking at. And this is because not all spirals are the same. And so we have two main types of spiral patterns. We have these ones that behave like a density wave, and these are typically what we would call a grand design type of galaxy, a very strong potential that rotates like a solid body. So the spiral pattern is a fixed one, rotates nicely, all with the same angular speed as it goes around the galaxy. But the gas itself, it doesn't. As I said before, it has a fixed velocity, linear velocity, which means effectively that the angular velocity is different depending on where you are in the galaxy. This creates something that we call the co-rotation radius. So at some point, your gas and your pattern are going to be traveling at the same angular velocity, but inside of that radius, the gas is traveling faster than the pattern. Outside of that radius, the gas is traveling slower than the pattern, so it's actually the pattern that sweeps up the gas in front of it. But these are not all spirals. You have these other spirals which have more transient or more dynamic arms. Actually, quite a lot of galaxies are more like this. And so this is what we call maybe more flocculent type of galaxies, where you do see a spiral pattern, but it's not long-lived. So these patterns change very quickly, very dynamically. They're not very strong necessarily. And so this really changes how your gas is going to respond to the potential, because it doesn't really have time to go in and out of the potential. The potential is changing as quickly as the gas is trying to do something about it. So you can have less strong shocks because the gas doesn't actually go through the potential normally. You can even have inflow into these arms from both sides of the arms, which is kind of weird. So yeah, so are molecular clouds any different then if we take this into account? And so we try and do this, tried and did this with one of my students here at Cardiff, looking at M51, and we used a new technique that we've developed to look at the gas surface densities from Hubble images using the dust extinction. And what this did was to give us a higher resolution than you can get from the molecular line observations. So we have, in this case, for M51, we have like 5 parsec resolution. So we're starting to get to see what's happening inside of these clouds, get to see a little bit more of the structure of these clouds to infer more of what it's doing to its properties. And so when Elena, my student, she did this, she looked at how the gas surface density of clouds was varying as a function of distance to the galactic center. And for this particular purpose, I just want you to focus on these two things. So the green curve, which corresponds to clouds in the spiral arms, and the blue curve that corresponds to clouds in the interarms. And you can actually see that they're quite different, but they're not quite different everywhere. They're just different inside of that red line over there. So this radius, where that's happening, is the co-rotation radius between the spiral pattern and the gas. And if I plot it roughly onto this image, you can actually see that the spiral pattern is quite different inside that radius as it is outside. In fact, outside that radius, there's no fixed pattern to this spiral. Because this is an interacting galaxy, the spiral arms outside the center are actually more dynamically evolving. They're evolving much more, even though they're quite strong and they look like a grand design, they're actually quite young patterns. And so we think that that's probably the reason why the gas is behaving so differently inside and outside of that radius. So inside, where you have a density wave, your gases had time to experience going through the spiral arm shock and enhance the densities of clouds that are in there compared to the interarms. While outside of that, you look at a cloud in an arm and a cloud outside, they're the same. There's no difference. So there's a hint there that maybe, depending on where you look, it might actually be doing something. And going back to the Milky Way and the fact that we don't seem to see much in terms of anything being different in arms and inter-arms, if we've looked, maybe this is telling us that the Milky Way is not that grand design spiral that we thought it was. Maybe the arms are more dynamically evolving than we thought. Maybe it's more flocculent-like. So just a thought, something to follow up maybe in the future. Can we tell anything about whether star formation is influenced by this passage to the spiral arms? Okay, we're piling up material. Is it doing anything to star formation? And especially if we're looking at the grand design type, which is the one that is meant to do more to star formation, you can imagine your spiral pattern. It's rotating at this fixed angular speed. And if you're inside that co-rotation radius, it means that your gas is going faster than the pattern. So if your pattern is rotating this way around, your gas would be coming into the arm through the inside of the arm. So you have your gas clouds. They enter the bottom of the potential. They collapse. They contract. They start to form stars. So you have young clusters in blue. And then as the gas and the stars then leave the spiral potential to the other side, then you start to get your older population of stars because they're starting to age as they leave. So for a density wave type of pattern, we expect to see stellar age gradients. So as you go through the spiral pattern, you expect to see younger stars in the very ridge of the arm and then the older stars as you move away from the arm. So do we see this in observations? How do we do this? So the first thing is you need to determine the age of your clusters. And you can do that by using different tracers. So you can use, for example, the UV light to trace the a bit older clusters, age alpha to look at the intermediate ones, 8 micron emission to look at the younger, nearly embedded ones, not quite. So you can use these tracers to sort of age your cluster, and then you can define your spiral pattern either using the stars or the dust lanes or the gas emission. And then you can look at correlations. So for example, in this image, you have for a single galaxy here, how the young clusters are distributed, how the intermediate age are distributed, and how the older clusters are distributed. And then you can compare whether you see that little shift in the position of these clusters. And the answer to whether we see this or not is that we can see them definitely in some grand designs, but not all grand designs. And even when I was doing this, trying to look through papers, see what they find, actually, for the same galaxy, you can get different answers depending on how you've done it. So it's really, what answer do you want to get? I'll get you there. So it's really, really frustrating. But what does seem to be the case is that when you look at more flocculent galaxies, there's nothing there. When you look at young spirals, there's nothing there. So there is the consensus that it doesn't exist on the more dynamical arms. For grand designs, maybe, maybe not, maybe on some. Okay, so that's just in terms of whether star formation is triggered with the passage of an arm. We have spiral arms acting as this meeting place for clouds. So you have more gas, you have more clouds, you have more star formation. You can see that clearly from the image in the background. These red stars are basically the young clusters. You can see they are in the spiral arms, right? So the spiral arms are helping star formation. But the question is it actually more efficient in the arms? Or do we go back to the original plot where it's just, well, we have more gas, so we have more star formation? Or is the star formation actually more efficient? So for the same amount of gas, are you forming more stars if you're in an arm, or are you forming the same amount? So is it enhanced? I'm sure you'll not be surprised to know we can't tell from the simulations because we actually use this as an input parameter for the simulations. We say, yes, our gas is 30% efficient in forming stars, or just 2%, or just 1%. It's really whatever you want to fit it. So in the galactic observations, we can see that specific regions are actually more efficient at forming stars. But because of what I said before, yes, these regions might be in the arms, but they're just a handful of them. So whether they're more efficient because they're in the arms or because of something else, who knows, right? And finally, extragalactic, yes, all sorts of answers, all sorts of galaxies. I don't know. We don't know what's going on. But on average, I would say that we seem to have, statistically, we have the same type of star formation in arms and outside. But it does seem to be a hint that for you to form the more extreme type of clusters, the more extreme type of stars, so the more massive stars, maybe there the environment is playing a role. So maybe the type of stars that you're going to be forming, like for you to form these big clusters, you actually need specific conditions. And these are only found within specific regions of the galaxy. And hope is not lost because, as Tim mentioned, we have JWST now up and running, and JWST is giving us now for the first time the ability to actually start to look inside the embedded star formation in nearby galaxies. So we can actually see the protostars or the protoclusters that are being formed within the clouds that are there now. And we couldn't see this until now. So this is some hope. Maybe call me again in a few years. Maybe I'll have an answer. I don't know. Who knows? So I'm almost done. So the last thing I wanted to sort of talk to you about the galactic dynamics is obviously, as Tim said, you have some spirals that have bars, you have some spirals that don't. So what does that do to a galaxy? What does that do to the gas? So actually, if you have a disk and that disk is unstable, it's going to evolve very quickly to form a bar to try and stabilize that disk. So galactic bars are actually quite a natural result of the attempt to stabilize an unstable disk because it produces a lot of turbulence that goes across. So the kinematics of a bar, they don't just influence that little section of the galaxy where you have the bar, but it does have resonances that go way beyond into the disk that can affect then what's happening to the gas. But I'm not even going there because who knows what these resonances are, so let's just keep it simple. Let's just look at what happens inside that bar. And so in a bar, you have gas that travels essentially along the length, I can't really point with it, but along the length of the bar with orbits that go back and forth like this. So you have a lot of dynamics that are slingshotting your material from one side to the other, and you're feeding that central zone with gas through these lanes of material. And then sometimes you then get that material to get caught up by the center, and then it has little orbits around the center of the galaxy that form what we call a central sort of molecular zone. Because of these extreme motions along the bar and even across the bar, these orbits, they give you a lot of turbulence into these clouds, so it's quite a hot environment. And there's also high levels of shear because these motions are so quick and so abrupt. And this changes the stability of clouds. So it produces levels of turbulence that help to support these clouds against gravity. So it changes how much star formation they can have. But actually, when you look at nearby galaxies, it seems that a lot of galaxies have enhanced star formation in the center, in those central molecular zones. So in a sense, because you have added levels of turbulence, your clouds grow and they're not collapsing. So when they do, then the star formation is super efficient because you have a lot of mass that is suddenly going to be converted into stars. So do we see this in our galaxy? Actually, no. We do have a central molecular zone, and we do have supermassive clusters in the center of a galaxy. But the current clouds that we have are just doing nothing. There's very little star formation there. Why? Actually, there's been the suggestion that maybe this is just a matter of time. right? These clouds, they are very, very massive, but because they're so turbulent, they're not collapsing under their own gravity. So they need that to be dissipated, and then when the cloud is then able to collapse, it will, that's our hope, then become a super cluster. So maybe we just caught our galaxy in the wrong time, or just to mess up our brains to why this isn't working for our own galaxy. But anyway, it does have a big impact on the type of star formation. So it does tell you that environment does do something to your clouds. Now I'm going to finish off by something that is not driven by the galactic dynamics, but it's something that's actually really important in the shaping and in the travel that your gas does around the galaxy. And it's something that Tim already mentioned, and I'm guessing maybe Nicolas as well, I don't know. So that is the feedback. So supernova and pre-supernova feedback. So the radiation from the stars as a cluster that they give back to the ISM, and then as they explode with supernova at the end of their lives, this is actually something really important. So it's not driven by the galactic dynamics, but because they're so extreme, they can actually impact quite large areas around that event. They input a lot of energy, a lot of momentum into the gas, and they can actually inject turbulence at sort of hundreds of parsec scale, so full cloud kind of scale. It's been suggested for quite a while that the supernova feedback and pre-supernova feedback is really important in providing the required levels of turbulence that we see in the ISM. But actually, so this is a simulation, and when people were looking at this in the early days, they were like, oh, these holes in the galaxy, we don't really see that in observations. This is probably way too big. Like the effect, because these are recipes in the models, like, you probably got it wrong. But then, observationally, until now, it was actually quite hard to infer the effect of these supernova explosions into the ISM in these large scales. But then JWST came along, and then it showed us this. And we're like, this is an actual galaxy, and you can see these bubbles that we were seeing in the models. And so actually, we couldn't see this in the gas, in the diffuse gas, but you can see this, sorry, in the dense gas, but you can see this now when you see the more diffuse, almost like ionized type gas. So they are there. And these super bubbles that we couldn't see elsewhere, they're just voids in space, but they are creating or changing how a galaxy actually is doing. So if you just look at the travel of the gas around the galaxy, it's not a smooth ride, right? It has all these bumps on the road that are just exploding. Or you can think of this as kids in the back of your car just screaming at you, and sometimes you go off course, and sometimes you're just building up turbulence inside you and it's just giving it cool. But it does make a big impact on your journey. So I'd like to finish that. There's lots of hope with JWST now, trying to pin down some of these things. And I'll finish here. So thank you for listening.
Thank you, Anna. We've had lots of analogies here. We've got galaxies as black holes as messy eaters, and now we've got galaxies as kids in the back of the car.
Supernova.
Screaming at you. Yeah. Yes. Any questions? You've had enough. You've had it. I'm sorry. They're exhausted. Yes.
What causes density waves? You mean in the spiral galaxies? It's due to sort of what we call orbit crowding. So because a star, as it rotates around the galaxy, normally it has a nice circular orbit, but because it actually has what we call sort of small fluctuations, it causes these orbits to be slightly elliptical, and depending on where you are in the galaxy, that orbit sort of crowds, and I think I might actually have something that shows that. So something like this. So you have these little orbits that are elliptical, but they kind of change slightly in direction as you go out in radius, and that means that your stars are going to crowd into that, into those places here where you see this enhancement. And then this, because the stars still travel with your nice velocity, the pattern just rotates nicely around. So this is what would cause a density wave. But real galaxies are more tricky.
Well, they are tricky because you repeatedly showed us M51.
Yeah.
But that's not a secular galaxy. It's
No, but it is
system,
it's so pretty. Come on.
Which is obviously having a big, that other galaxy there's obviously having a big
it
impact
is.
on
Yeah, so
what's
it's
happening.
impacting the outer arms more than the inside.
Any other comments? Yes, over here.
Yes, I can tell you that. Yes. So when let me show you this. When I showed this plot over here, I'm gonna leave this. So I hope you can still hear me. So this part here, these motions here, and the motions of the gas along this part, this has to be from the gas going in the non-circular motions of the bar. So we know for sure there is a bar. How big? How it's directed, but it's there. Yeah.
Good news, there's a bar.
There's a bar.
Right. Anything else?
Do we still have to pay at this bar?
It's free, as far as I'm concerned.
Nothing really free, is it? Well, we'll thank you again.
You're welcome.
And yeah, very dynamic presentation of these dynamic objects.
Thank you.
Right. To conclude, I have to thank various people today. Thanks to the National Museum of Wales, and in particular to Christian Morris for facilitating the use of the venue. Thanks to our technician, who's Tobias over here, Tobias Goff. And he's been doing a recording, and we will put these talks, if the individual speakers all agree, we will put the talks on our BAA YouTube channel eventually. Thanks for the refreshments were conjured up by Erin O'Dare-Smith, and the Welsh cakes are absolutely lovely. So worth coming all this way for those. Thanks to all of our speakers, Doctors Titley, Doctors Peretto, no, it's you, but Doctors Peretto, Birkinshaw, Schmidt, Davis, and Cabral. Thanks to the Cardiff Astronomical Society, their chair, Philip Wallace, Secretary Greg Titley, and Public Events Coordinator, Teresa Cooper, for all the work they've done, and also other volunteers here, Joan Payne, Catherine Compton, Siobhan Conlon, Jane Clark, and Bob Bliss. And thanks to the BAA office and our systems manager, Andy Wilson, for their help setting up the admin for the meeting. Most of all, thanks to Hazel Collett, who's at the back here, and Hazel and Graham Collett, who's described here as the PA to the meeting secretary. She's never described him as that before. He is obviously her husband. A round of applause for Hazel and Graham. I hope to see you all at another meeting sometime, and safe journey home. Good night.